Okay, thank you very much, and thank you the organizers for letting me to attend this workshop. Well, my first day in Dublin, but first day in this institute.
Concerning the later I asked, sorry. I had a non-scientific question.
Yeah, so my topic is probably off the track topic of the meeting. But, so please stop me if there's something which is my talk is actually in a way in two parts. In the first part, I will talk about this some particular kinds of loop models on these particular kinds of triangulations called causal triangulation. And in the second, and then there will be a correspondence with the trees, which can be used to not solve these models, but actually to analyze these models. And then in the second part, I intend to say a bit more about these trees and also explain some of the concepts in the first part. But it doesn't really matter if I can't make the second part, so please don't hesitate to ask. So maybe I should just start by introducing the models, and then I can try to explain the way of what the purpose is. So, so these are loop models on causal. So a causal triangulation is triangulation of a disk of this particular kind. So it is layered. So it consists of circles which are referred to as spatial slices, and then we have triangles inserted in between. So these are rather particular types of triangulations of disks. So these were introduced by Jan Andrian and Dr. Dahl in 1998 as a kind of approach to quantum lattice, to discrete approach to quantum gravity.
Sorry, I have bad hearing, I admit, but
okay,
can you talk a little loud? I just barely hear you, but I'm worried that the people in the back will not.
This model can be considered as a restriction of a more standard, the Euclidean triangulation model, where there's no restrictions on the triangulations except that they are plane. And one would hope maybe then one could analyze this model in more detail, also in higher dimensions than the Euclidean models. But actually, it turns out that it is not much easier, and actually, less is known about statistical and mechanical models on these triangulations than on the general Euclidean triangulations, because there are the matrix model techniques which are very effective in that case, not apply in the same way in this case here. What are the idea, what I'm going to talk about are actually statistical models on such triangulations, coupled to such triangulations. So these are random triangulations in the sense that we allow the triangulations to be arbitrary. And then to introduce the models, I will consider our loop models, and that means that we insert certain loops on.
Just going back, the causal thing. These are the red circles, or
yes, the red circles are referred to as spatial slices, and then the radial direction is usually called the time.
Yeah.
Time direction. But although everything is Euclidean here, there's no because.
What's the definition of causal?
So this is just a name that these people introduced because there is this time direction. So in a way, I mean, it refers somehow to that there is a global time possible to define a global time here. This is not the case in more general triangulations where you can have outgrowths, so there's no well-defined direction of time. So this is what this is the reason they introduced this causal. one tenth.
And then how did the next set of dots are placed randomly on a circle? Is that what it is?
Yes, I mean the dots are, but there are some restrictions. I mean there's no restriction on the number of dots, but there are, of course, it has to be a triangulation in such a way that there is one vertex of a triangle on one space slice and two on the other one. So they're not. You cannot have degenerate triangles in the way that you can have all three vertices on one space slice. Yeah. So I will discuss actually two types of loop models. So these are loops on these triangulations, and they are composed of, and they're obtained by inserting certain configurations of arcs on the triangles. Okay? So in this, what I call the dense loop model, the triangles can be decorated in 4 different ways, 2 different ways actually, depending on forward directed or backward directed triangles. So all triangles are decorated, so that means actually that all triangles are filled somehow, and so the loops traverse all triangles. That's why it's called dense. Okay. So by introducing this, you get a certain set of loops here, and I will introduce weights on these loops, which are sort of canonical. So script L with the DVD upstairs is just a set of all dense. So when I call this the element, I call L, but you should remember that this L consists both of the triangulation and the loop configuration. Okay, and maybe I should have called it C comma L. I don't make the notation too complicated. So numerical value L is simply the number of space-like edges. So that means the number of edges on these horizontal edges, circular edges, and these are simply related to the number of triangles. They're simply half the number of triangles because there are 2 triangles in each spatial edge, and that is so what we call the area. And then there are 2 types of arcs. There are the time-like arcs, which sort of go from spatial link to a time-like link, and then there are the space-like arcs. These go from time-like links to time-like links. Right? Okay. And what we do is to associate a weight factor G to 1/2, as I mentioned here, to each triangle, or to each triangle, and then another weight factor to each time-like arc. Okay. So not to all arcs, but I could also actually also put in all arcs because there are 2 relations between the length of the loop, which is simply the number of arcs, and the area, and also the horizontal loop. So I mean, one can choose any of these 2 variables. I mean, the number of loops and the number of triangles, or choose the number of horizontal edges and the number of spatial edges as variables.
So you start with a fixed triangulation and you calculate the partition function of this fixed triangulation.
Yes, yes, that's true. Yeah, I calculate the partition function corresponding to a fixed triangulation by summing over all loops for this fixed triangulation, and then I sum afterwards over all triangulations.
And you did not define what is the height M.
Sorry?
You did not define what is the height M.
The height. The height is the radius. Sorry.
Oh, okay.
Yeah,
So,
yeah.
but that's
the number.
the radius is fixed by the triangulation already.
Yes.
Was that called H of C in the previous one?
Yeah. I have actually mixed 2 types of H's. Sorry. Yeah. So the height. I'm going to make a correspondence with G's afterwards, and then I will call them the height. But it's the same as the radius, the number of slices.
So the loop models are meant to represent like vector models or vector models like they would do.
Yes, I mean some kind of statistical models. Actually, I will say a little bit more about. I mean, this dense loop model is not so obvious what it is related to, but the second one is more related to the Ising model. Actually.
Oh.
So, yeah. Yeah, so the partition functions are actually defined in this way. So as you said before, I mean, the sum over all, these weight factors over all possible decorated triangulations, okay, over all loop configurations, including triangulations, okay. Yeah. Now, so this was the first model. Then the second one is different, where you only allow decorations of this one. So either there's nothing in the triangle, or there is a single loop, a single arc, and this arc can either be space-like in the first one, because it's sort of parallel to space-like, or it can be time, but only one. So here is an example of so some triangles that they can be empty. So that's why we call it the direct loop. But otherwise, the partition functions are defined in the same way here by introducing. I mean, the weights are the same. So it depends only, as I said here, on the time-like, on the number of time-like loops. So we don't take into account space-like, which may be a little strange. Because in this model here, we don't have the simple relation between the L and the T and the S. And we cannot express S, that means the number of space-like arcs in terms of the area, and the time-like arcs, because we allow empty triangles here. But this is the model that we consider. So as I mentioned before, it is maybe good to think about this as a restricted easing type model, because if you define instead a more general type of model, so next slide here, this one here, it is not hard to show that this is actually another way of writing a kind of anisotropic easing multiplication function on the triangulation. In an easing model, you have triangles, and on triangles, you can have spin configurations here where you have either you have all spins equal, then there's nothing that corresponds to the empty strings. Okay, they're all equal. Otherwise, you have two pluses and one minus, or vice versa. And here you have contributions. I mean, these opposites here, opposite signs here give rise to a plus one factor here corresponding to a time-like edge. And this one here also gives here. So if you draw the arc here, then you get and you actually associate a factor, say alpha with this vertex here, and beta with this vertex here. So you get the factor of alpha times beta with this time-like arc. Okay, that is this one here. Whereas if you have the other integration, that you have equal signs here, for example, plus here, minus here, you will draw this bit here, and you will assign still a beta here. There's
You are not restricting to discrete plus and you're not summing over plus and minus variables as in the spin.
Yes, what I'm claiming is that sum over plus and minus variables to sum over configurations. If you make these assignments, you assign.
You're assigning a weight to each of those diagrams. It looks actually more like a timer model to me.
No, it's actually not. I mean, because the spin configurations they determine. These are just spin costs. I mean, the boundaries here. I mean, the loops are in the spin boundaries. Right? So you look at clusters of pluses, and then you draw, a loop around it according to this convection here. Then you get an energy which is actually proportional which is actually equal to this But this alpha is equal to, say, I mean, this is anisotropic, maybe anisotropic. Alpha is equal to beta, it's anisotropic. The model, right?
Yes.
The easy model.
It's more like an annealed spin class, like that, right? So you're on a triangular lattice.
Yes, I mean, the random triangulation, then you can think about it that way. Yes, yes. So actually, in the model I was writing down, it said wow. So that means that you have no rates for these horizontal arcs. Okay. I mean, there is of course a reason for doing that because it turns out to be difficult to. I mean, the easy model has not been solved in these random triangulations. So it's an open problem. So you can think about this as a kind of restricted, strange, maybe a little bit strangely restricted, because I mean it corresponds actually to put beta equal to 1, corresponds putting. I mean you have into temperature, into zero coupling in that direction. Yes. Okay. Is this more or less? Did I answer your question?
Yes, I think so. I'm not absolutely sure because there's a loop representation of the dimer model as well, and you can represent the easing model as a particular formulation of the dimer model.
Well, so maybe it's the same thing that you're thinking of. It depends on exactly which dimer model you're thinking of.
Yes.
The beta here is, I mean, you can think about beta as, if you think about it in terms of the easing model, it is e to minus the coupling along these time-like edges. So you have e to minus g beta sigma I sigma j. Then you should probably subtract 1 from what to get a 0 contribution for that. But then you can absorb into the g part. I mean, the number of triangulations. So it's not true. A redefinition of this, but essentially beta is equal to this. This is the time by coupling, and alpha is equal to e to minus the coupling of space-like edges.
But it's important to count alpha and beta different.
Yeah, in my case, I will actually mostly put beta equal to 1, and of course not alpha equal to 1 because otherwise.
Why do we don't have this kind of diagram in the dense?
Because in the dense model you don't have them. You have these two. You have two arcs in some triangles, but they don't correspond to. You mean what you mean with there you want to use two different couplings for the time-like space-like. Is that what you're thinking about?
That too, and also why in the dense configuration can we not have just one bench in the corner like this? Like if you introduce this.
Yeah, that's simply a convention. So I mean these types of loops models you only have. That's just a convention. But the other question about having different values of alpha and beta is not. It's not a generalization of the dense loop model because there are these relations between the time-like and space-like number of time-like and space-like edges and the area of the surface. So you don't need to have more than 2 coupling constants there. Yeah.
And here you're considering equilateral triangles.
Well, I mean these triangles are I mean we think about them as equilateral, right? But so there is no length associated. Abstract relation.
Yeah, I'm just asking that because in the previous slides you wrote down a relation and say that the number of triangles is equal to the area of the conflict.
Yeah, and the area is just a number. It's just by definition a number. So we think about them as equilateral if you want. Yes. Yeah. The same contribution to the area. Okay. So there is a well-known correspondence between triangulations of this type here, a very simple correspondence, and planar trees. That means trees drawn on the plane. And it is obtained by, I mean, maybe it's not obvious, but if you have given such a causal triangulation here, and you delete all these spatial links, all the links on the spatial slices, and then say, for example, the rightmost link emerging from a given vertex, it turns out you get the tree, and you can reconstruct the triangulation from the tree. Maybe not completely obvious, rather obvious. It is actually a restriction of a much more general correspondence between trees and triangulations. This is a very special. So in that sense, one can say that this restricted dynamical triangulation approach to gravity is actually, it's a model of trees, basically, at least in some respect, depends on what you want to do. But the combinatorics is that of trees, which is well known. So here, I just describe this. So this is just a description.
Is the map of the trees true in higher dimensions?
No, it's much more complicated.
Right.
Yeah, no, it's very special to do the mapping. So here, just a description of this mapping, and the point I want to make is just that it is easy to extend this mapping to these decorated triangulations. You can simply decorate, I mean, add a label to edges in such a way that if there is a time-like arc which intersects a space-like edge, then you insert a label 1 to the left of it, to the vertex which is left of it. So here there is an arc. This, then you put the vertex label 1 here. But otherwise you have 0. Okay. And it turns out that it's not completely obvious, but it's also not very difficult to see that if you do that, you have a one-to-one correspondence, not a one-to-one correspondence. There is a correspondence between the dense loop configurations and these decorated trees with the labeled trees, and also it extends to the dilute loop model. But there is a restriction on the labels in the dilute case, where the number of ones in a given spatial slice should be even. But this is not so difficult to see, because if you look at the slice which is closest to the center, then there is an even number of loops, because all the loops they either go from the slice to itself, or they go from the first slice to the next one. Right? Okay, so on the first slice there is an even number, and then it's not difficult to see that this parity is actually preserved along the way, because loops, they may either go from one slice to the next one, or they go back to itself. Right? But in the dense loop case, you don't have this restriction, because you don't have even and odd numbers. You have two. I mean, all triangles are decorated, and you have two arcs, two time-like arcs, if there are any. So there's no restriction. So this correspondence extends in a simple way to that, and that can be exploited.
So sorry.
Yeah.
Can you explain the algorithm in tree from model?
Yes, that is what I try to describe here. Okay, so if you're given a triangulation, you first take it and remove all the spatial links and all the edges on the triangles. Okay, and then you look at each vertex, the outgoing edges from each vertex, and you remove the rightmost for example. You can also do the leftmost. But just by you need to have some procedure for removing one of those ends. And then it turns out you get the tree. And this can be legal. Right. Okay. So I have written here this that the first, I mean, for the dense loop configuration, this correspondence is bijective. But for the dilute ones, it's not bijective. Simply because there is a freedom of this choosing this. When we're given a label here, one here, you know there should be an arc here, but there is a freedom in choosing this arc to be this one or to be that. You have to make one of those choices for each slice, and that gives rise to this factor of 2 to the n, which actually turns out to be important for what I'm going to say. But otherwise, we can write then the partition functions for the loop configure these loop models in terms of trees, labeled trees in this way here. So notice there is this additional factor 2 to the n. Otherwise, it's just the same here, and we sum here all only over these even labelings in the pattern. But here there is no restriction, so this is okay. And then we sum over m, then we get the sum, then we get the full partition function, and here we get then the sum over all triangulations. We lose this restriction, and so that means that we get we can express the partition functions of original model in terms of certain tree partition functions. And the reason for doing this is that the combinatorics of trees is easy to do. Essentially, everything is normal. So
these are all rooted trees because your root is the origin.
Yes, yeah, it's a little bit more complex. I forgot to say that my root is actually not equal to the origin because you had to add a link. You had to add an edge, an extra vertex. But this is a detail, which is not, I mean, in order to get this correspondence to be exactly, but it's essentially the same. Yeah, so the tree model, I mean, this is just a rewriting of the previous equation. For the dense model, you have this very simple relationship. And here you have no restrictions on the labeling. So you can sum over the labelings immediately. You just get an additional factor here, which only depends on the size of the triangulation in the area. So you get the 1 plus alpha squared. This is just a sum overall. It's a trivial sum.
But since the unlabeled, the basic construction is that of trees, I guess you can't access with these causal dynamical triangulations. You can't access the usual 2D quantum gravity model. You can't get the right spring susceptibility or anything. Stuck in the phase of branch columns. Is that right?
Yes. Well, yes. In a way, that is true. Yes. I mean, you can certainly not reach the universality class of the Euclidean.
So you can't access
No, for that you need a different correspondence. I mean, there is a different correspondence there where you also have labeled trees, but the labeling is more complicated there.
I see. So
but you can do it. I mean,
the vanilla model, no, you really can't access the usual matrix model instructions of 2D gravity there.
No, you mean these causal triangulations? No, I mean there do exist some matrix type integrals, but they're not as attractive. I mean, they're simple. No, that's true. Yeah, and here, I mean, here this W here. So for the dense model, we don't have to do very much more. I mean, you can just. I mean, we found out that this is just given by the partition function for the trees, which is defined here, which can be computed explicitly. I mean, this is known for a long time. And this has a square root. So this function here, you should notice. I mean, this has a square root singularity or branch point at the g equals 1/4, and correspondingly, this one have a singularity and some shifted point here. And this singularity determines, not everything, but determines, for example, critically, what is called the Hausdorff dimension that I will introduce a little bit in a moment. But the singularity of this function here, the function of g for fixed alpha, is the same for these trees. That means the same as for pure CDT, causal dynamical. But for the dilute case, I mean, it is more complicated. We actually have this height coupling here. And so we have this factor 2 to the height. And we also have this restriction to even triangulations, so or even deltas. So that means that we have a factor of this type that this picks out the even powers of alpha for each slice. Okay. So I introduced the notation ni, the number, which is height or radial distance from the center. Okay. Yes. So we will need to consider this height. This is what I call the height coupled tree. So that means, I mean, the usual trees only have a weight factor which depends on the size of the tree. The size of the tree is actually the sign. The size of the tree is the number of vertices, either vertices, or it's more usual to use the edges. But this is essentially equal to the area of the corresponding triangulation. And then we have here an additional coupling to the height here. So I call this coupling K. So this was equal to 2 actually for these dilute triangulations, dilute. It turns out that this K factor here is very significant with respect to the critical behavior of the partition function. Namely, if K is less than or equal to 1, it just remains as I mean, the critical point is the same as if you didn't have this factor here. Whereas if K is bigger than 1, then you have a different, it shifts the critical point, but also the singularity is completely different. You have a simple pole instead of a square root branch point in this case, which gives rise to a completely different critical behavior. So just to be short, I mean, let me just describe what results we have. So I will just talk, I will not discuss any two-point functions or spin correlation functions here. We're only interested in how the critical behavior of the model, of the statistical model, influences the geometry of the circuits. And for that purpose, we define what's called the Hausdorff dimension, which is simply the exponent of R. I mean, if you look at you look at a large triangulation and you look at the ball of radius R around the center, it increases as a function of the radius with some power. Okay, and this power we call the Hausdorff dimension. So, of course, if you are in flat regular triangulation, this is 2. But since the triangulation is random here, it's different from 2. For example, if you calculate the average value of this quantity here, may be different from 2. But we should remember that in order to calculate this quantity, we can also do it in terms of the trees, because the vertices in the tree and in the triangulation are the same. Okay, so the area is of the triangulation is proportional to I mean, of the ball, the radius r is proportional to the corresponding ball in the tree, okay, measured from the root. So in this respect, you only need to do the calculation in the tree. Now, of course, here in order to make this well defined, I mean, you have to have a large triangle. You have to have large triangulations. That means that you have to approach the critical value where large triangulations start to dominate, and then you have to make the disk large. Okay, so this is not very precise. Exactly, there are some assumptions behind it. I will make it more precise in the second part. Get that part. Okay. It is easier. I mean, the right way to do this is actually to take the infinite volume limit, then it's a proper definition. That can be done. So, as I already mentioned here, in the dense case, I mean, there's nothing new happening here. We get the same critical behavior of the partition function, and that actually implies, it's not obvious often, but the DH here is actually determined by the critical behavior of the partition function, and it stays the same. And this is actually quite well known to be true in this case.
Sorry, I'm confused. So how did the notion of height come about from the original Bootstrap?
You mean how I define the height, or
Yeah, the definition and how it appeared naturally.
the point is that it appeared in this dilute model here.
Yeah.
You had this where it was 2, so there is this factor of 2 coming here. Okay? So that's why we're interested in this. And we have to include this factor here.
And the
So-
definition of the height is
The height is our triangulation is just the maximal distance from the root to a vertex. Okay, and it's also for the corresponding causal triangulation is simply the radius, the number of spatial slices, the radius. This.
then you generalize the model to k equals not.
Yeah, then I look at a more general case. I don't put k equals to 2 because it turns out to be quite interesting to look at general k.
Okay.
And that is actually the topic of my second part of my talk. But here it's only k equals 2, which is
And the k equals 2 case belongs to the second.
exactly. It belongs to the second part, where the partition function is as a simple pole. And that that is what I was going to mention next here. So in the case where you put alpha equal to 0, okay, so alpha equal to 0, then you only get this high coupled tree. You get exactly the high coupled tree with k equals to 2. Okay, and then you have the simple pole, and it turns out that if you do that, well, I mean, it turns out that this means that the Hausdorff dimension is not 2 anymore; it's actually 1. So that means that actually the triangulations are very degenerate. The Hausdorff dimension. Now it turns out, and this I'm not going to show you here, but it is actually possible to analyze this model in the vicinity of alpha is equal to 0. So you can make alpha different from 0 and use. I mean, it turns out that this model is analytic in alpha in a neighborhood of 0. So the method you can use is a transfer matrix method. And you can look, and it is a transfer matrix approach, which is actually also well known for the causal dynamical triangulations, but it can be generalized to this case here, as long as b is equal to 1. And you can, I mean, the point is that you have to analyze, and the critical behavior is determined by the largest eigenvalue of the transfer matrix.
How does the transfer? I mean, you're transferring in the
Yeah, in the radial direction. The radial direction, yes.
Something like a triangle.
Yeah, you have triangles inside. So you have to sum over the triangulations inside, or you have a triangulation inside, and you sum over those triangulations, but you fix the number of edges in the two neighboring slices.
Okay.
And use those as variables. So it's an interdimensional transformation, but it can be analyzed, and that is what we do in this paper with these people here. And it can then it turns out that this critical behavior here actually persists in the vicinity of alpha equal to 0. But we don't know how large this neighborhood is. So the conclusion actually is that there are two possible scenarios. Either this value of alpha is equal to 1 all the way up to alpha is equal to 1, but certainly not equal to 1, because when alpha is equal to 1, we know that it's equivalent to pure gravity, where it is equal to 2. And the other option is that it's actually only persists up to a certain critical value. And this is the scenario one here. So here I have sort of indicated the whole diagram of this easing. We have this easing model, anisotrophic easing model. And we are only looking on this line here. This line here would be very nice to look at. Looks pretty simple actually, but you cannot. We don't know any way to do this. I mean, transform matrix doesn't work. And also, there seems to be, it's not clear that there is any analyticity in beta here, exactly because of this this strange behavioral shift of the critical point from 1/4 to something which depends on bias. I mean, this beta is somehow, contributes to the height weight. But if there is, say, a critical point here, I could imagine that there is a critical line going from this point to this point. And therefore it doesn't hit. Well, we don't know. It could also go this way here. The point is that nobody, all investigations of the isotropic easing model so far have see no signature of any transition here. Contrary to what happens in the Euclidean model, where it is known that you have a critical point where the critical exponents are shifted. But so far we don't know. There are many unanswered questions.
Why is the whole dimension always in differ?
Sorry?
Why is causal dimension always in differ?
Oh, that is not known. It doesn't calculate.
Both here, 1 and 2.
Yeah, here is known. I mean, I know that you can calculate it.
Oh, I see.
So here is known to be 1, but at this point, so here actually strictly speaking, I only know that it's 2 here at this point here. But here it could also vary continuously.
Oh, okay.
Potentially, it could. We actually don't know. Yes.
I mean, it should not be too difficult to do numerics to distinguish between the two possibilities.
No, that is true. I think so. But nobody looked at it.
I see.
Okay. So far. As far as I know, they only looked at this line here.
Okay.
Which is very nice.
On this line of data, it was one that causal dimension changes continuously.
We don't know.
What?
Well, I mean, what we know is that it is constant equal to 1 in close to alpha equals 0. And we expect it should, we expect that it remains constant. But here, at this point here, it could be something in between.
Okay.
I don't know. I think it's not quite unlikely that it will change continuously here. But here it could certainly have some intermediate. Okay, so these were the results we had for this model. How am I doing in time?
You have only 12 more minutes.
Okay, but this I can explain this. So this second part of my talk is actually to explain or to put into perspective some of the things that I talked about before by looking at trees in more generality here. And in particular to emphasize this infinite volume limit. So we're looking at the tree models, and then let me first describe very briefly what is well known, namely the standard tree model where you don't have any height content. So we have these trees here, or a certain number of edges here, and we can turn the set of trees into a nice space where you can apply standard probability theory. Namely, to measure the distance between two trees in terms of the size of the ball on which they coincide. So the larger the ball is where they coincide, the shorter is the distance. So if you take the maximal ball, the radius of the maximal radius on out to which they coincide, you define the distance to be, for example, the inverse of this radius. This is what I have written here. That the distance between two triangulations is the inverse of the radius of the maximal ball on which they coincide. Okay, this is a quite natural way of measuring distance between actually not only trees but graphs in general. It's a much used distance here. But it actually turns out that this that if you include the infinite trees here, I mean there's no problem in having infinite trees here. If you include them, you get a very nice space. So this is a metric here, and it is nice, and it's an ideal space for defining probability measures. So that we can do, and you can discuss convergence of probability measures by just saying that the one measure converges, sequence of measures converges given you if the volumes of the balls converges. Okay, it turns out that this is equivalent. Integrals of nice functions converge. But it's very concrete, and you can actually use this very efficiently. So one way of defining measures, so the idea is to define measures as I did. Actually, I defined partition functions before. So you can define measures on finite trees, and then take the limit. So you define just in the usual standard way in statistical mechanics, a measure on finite trees, and then one can take the limit of this inside the space. So a standard way to define measures on finite trees is to use branching probabilities. So you associate with each n, which you should think of as the edges emerging from a given vertex, a certain probability of having this number. So Pn is simply the probability that at a given vertex you have n edges, n branches sticking out. Okay, and the sum of these should be a probability. The sum must be 1. Okay, and this defines a so-called branching process, right? If you think about the number of vertices on a given height or on a given slice of our triangulation here, as individuals, I mean, this describes the evolution of our population. Okay. There are two possibilities: either the average offspring is equal to 1, or it's less than 1, or it's bigger than 1. Okay, and it's clear that the behavior of this process, or the number of individuals as a function of time, will depend quite crucially on this value. So if m is less than 1, then it dies out rather fast, exponentially, in fact. Whereas if m is bigger than 1, it explodes exponentially. But in the limiting case, m is equal to 1, you preserve the average value since it stays at 1. Okay. And if you look at it in terms of the quantities that we already have discussed, so you define the partition functions just as the weight of these finite trees, just by taking them together. So these probabilities for each tree here over all the vertices in a finite triangulation, and you define the generating function like this. then the behavior of this set n is actually determining the singularities of this function here. So the asymptotic behavior for large n determines the singularities of this partition function. So normalizing with this partition function here, we get a sequence of measures. Okay, and you can take the limit. And it turns out that this limit exists and can be described in full detail. And I think I'm not going to give you all the details, but let me take just one example, which this is the primary example we're interested in. If you choose Pn to be equal to 2 to the minus n plus 1, then it turns out that this corresponds to the uniform measure on triangulations over fixed size. So you have the same weight assigned to each tree. Okay, and the limit of this measure actually exists, and it's very simple to describe. I think I'm not going to discuss really what is important here. We can skip this part here. That the important part is that if in the generic case, for example, in this uniform case, you have a square root singularity of G, and then now here these things are normalized such that the critical value of G is 1 here. I mean, in the previous cases was 1/4, but it's a question about normalization here. But this is the same square root as we saw before for the pure gravity model here, because it's equivalent to this tree model. And the behavior of this set n is exponential. So there is this G is equal to 1 here. There's no usually there's an exponential factor here, but it's not here because normalization has been done since the council. But then there is usually a color correction, and this is pretty universal in this case, n to minus 3/2. For Euclidean triangulations, this would be n to minus 5/2. So this is the difference. But the limit here, the limiting measure that we get, the limiting distribution of large triangulations. So when we take this limit, we're only looking at large triangulations. So this limiting measure will be a measure on infinite triangulations. Okay. So what do they look like, these infinite triangulations? Well, they look very simple. Or these, sorry, now I'm talking about trees. The trees look like this, and they have a single spine, and then there are finite branches sticking out. So there is a single infinite spine, and then these branches here, they are distributed actually in the same way as the finite trees that we started out with. And once you have this picture here, I mean, this is a well-established picture. I mean, it was proven in this form here by me and Hikaru and John Wheeler quite some years ago. But the similar results have date back to the 80s. And I think Harry Custom was first to prove this form. But once you have this, you can see immediately this Hausdorff dimension coming out, because these objects here, they are distributed, I mean, according to this branching process we had before, I mean, the original branching process, where there's one individual each side, at each height, okay? So if you calculate the number of vertices in a tree like this out to distance r, you have to take into account that they also grow out. And that gives the square root. The square of the distance, the ball in such a tree here grows like the square of the radius. Now, what happens in the height coupled case? Very short. I think I have 1 minute left.
Yeah, exactly.
Okay. What happens in the height coupled case is quite different. Lately, so here the measures are defined in this way. And depending on so in the case we were considering, this theta is actually negative. So e to minus theta was equal to 2 in that case. So when theta is negative, it turns out that this measure, the limiting measure, is still supported on trees with a single spine, but the branches, they are subcritical. So in the sense that that they are very short. I mean, the number of vertices in the branches is decaying exponentially. Okay, so therefore, so there is essentially only the spine left, and this is why it has dimension 1, positive dimension, essentially. Okay, and then just a final point. The most interesting case is actually when psi is bigger than 1. Because in that case, it actually turns out that the limiting tree is not anymore a single spine tree, but it has a much bigger spine, which is multiple spines. And you can analyze this, it turns out, in complete detail. I mean, it is a very, very well-defined limit that one gets. And the Hausdorff dimension in that case is 3 instead. That is because when you have this high coupling, you sort of suppress the growth out, so you sort of force the tree to grow out horizontally instead. And then the opposite is the case with this. So actually, yeah. So just to find out. So actually, what happens is that so there is this very nice transition picture here that for zeta negative you have single spine and dimension Hausdorff dimension 1. Then there is a transition that the zeta is equal to 0. You still have a single spine, but the Hausdorff dimension increases to 2. Whereas when you go to zeta bigger than 0, then you lose the single spine structure and the Hausdorff dimension. So this is.
You can read the questions.
The questions, yeah. Well, there are some questions. There's lots of questions, of course. I mean, there are also different notions of dimensions. I mean, this Hausdorff dimensions are a very special one, which does not take very much into account the internal structure of the triangulation. Here we had that, for example, the Hausdorff dimension of the tree and the causal triangulation is the same. But if you look at other notions of dimension, for example, what is usually called the spectral dimension, which is related to the Laplacian on the triangulation, it turns out that they turn out to be different. I mean, this is related to the return probability. The easiest way is to think about a random walk on such a random triangulation and the return probability to the center, for example, and the way it decays as a function of time. Then that defines the spectral dimension. And the spectral dimension of the tree is actually 4/3, whereas the spectral dimension of the causal triangulation is 2, equal to the Hausdorff. So spectral dimensions of these, for example, these various multi-spine trees is not known. But it should actually be possible to analyze. And also the last question, I don't really know whether this multi-spine tree actually plays a role, whether it can, for example, be realized by introducing other types of statistical systems, spin systems, or statistical systems on a triangulation, or maybe on some other triangulations. So we only had this correspondence where this K was equal to 2. And also, I mean, this multi-spine tree was also defined here only for this particular case where we have equal weights. I mean, for the equal weights up to this height dependent weight. How it generalizes to more general trees. I mean, where you have other types of branching probabilities is also not. Okay.
Okay, thanks very much, Bergfinnur.
Okay, thanks a lot for the invitation, and thanks for everyone for being here. Sorry, I have a bit of cold today, so I'm wearing a mask. So this talk will be about the Bootstrap method in the BFSS model, or more general, animatrix quantum mechanics. And the the main claim we want to show is that the Bootstrap method is could be the best numerical tools to study the large N dynamics. So this work, it is work last year for the Bootstrap of the BFSS model, and upcoming work maybe this month or in the latest next month, it will be about some two matrix quantum mechanics Bootstrap. And it is collaborated with my nice collaborator, Henry Lin, who is currently a postdoc in Stanford University. So I will try to be, I will not be very historical, but I will try to be as self-contained as possible, try to explain every logic details. So basically, Bootstrap method, what is it? It is trying to solve the problems in theoretical physics using the optimization theory. So that the central problem is, suppose for a model, we have some theoretical understanding, and we want to take advantage of it in our numerics. In some situations, this is not good. In some situations, this is not possible. For example, if you have some critical phenomenon, and you know that there will be emergent conformal symmetry, but very few numerical methods can take advantage of the emergent conformal symmetry because you cannot make it built in your algorithm. But that's why Bootstrap method can be the best method in the studying the higher dimensional conformal field theory. Okay, here is the thing. So we are taking the constraint, that is what we know about the model, as some constraint in the optimization theory. Then we try to maximize and minimize some dynamical quantity. The hope is that our maximization or the minimizations, upper bound and lower bound, they are pretty close to each other. Then we claim that we almost certainly know all the details of it. So here are some very easy example of the optimization theory that is, you may know it in junior school or high school. But our central interest is semi-definite program, that is the linear STP as a constraint. These appear really a lot of time since we have a Hilbert space. Okay. And I don't think I need to explain too much to this audience because there is really already a lot of expert in this matrix quantum mechanics stuff. And this is our central target for the Bootstrap in this whole line of project. Okay, but let's don't focus on the BFSS model, and we try to be more general and be more pedagogical to say, let's start with why doing the Bootstrap for this specific model. So the most standard method before is Monte Carlo method, that is, but the Monte Carlo method, it has some something we want to improve. The first thing is that in the large N, we know that physics simplifies in the large N. But in Monte Carlo, large N is not easy. You need to do some very large N extrapolation. You know that for very big matrices, even the matrix multiplication, it will be very small. To give you a benchmark, something like a 2000 matrix times a 2000 matrix, the matrix pure, the matrix product, each time it will take around order of magnitude 1 second. So larger is not easy. And in this specific model, Monte Carlo also encountered the problem of the sign problem, and you also need to do the finite volume truncation and also the finite N truncation, which is not pretty nice. But the Bootstrap gives you a much better idea that it works in the large N directly. We don't need to assume there is a specific N and takes N to infinity. We are starting with N at infinity. And it gives rigorous bound at rigidity. And there is no sign problem, and you don't need to do no finite volume. Okay, so one of the previous projects that shows how good Bootstrap works good in the larger limit is 3 years ago already with my PhD advisor, Vladimir Kazakov, and me. on the multi-matrix model. That is, we have a two-matrix model with in the permission matrix. And this model is not solvable, but at G equals H equals 1, with some bootstrap cutoff, you get some very precise determination of the moment. That is equation 9, you see there is something like 7 digits or 60 digits result. So what does this plot mean? This plot, the x-axis, sorry, it is not very clear. This is T2, which means
Sorry, I missed what lambda. What was lambda? Sorry.
Lambda is, you can think of it as we put some truncation on all the moments we are considering. So this is the length of a moment. Lambda equals 11 means 22. So we are considering all the moments up to length 22, considering all their cyclicity, their loop equation, their positivity, and it will give such a allowed region. So here there are different lambda. So you are increasing the lambda, you see the allowed region, it is shrinking quickly. A very tiny element. That's how we determine the operator in this.
It is the number of x's.
Yes.
Yeah.
Yes. And I will be more detailed. Don't worry. This is just to convince you that at least in some larger model, it works pretty much. Okay, let's begin with some toy model. That is, some people call it the memory model.
When you say pretty well, do you mean that you can obtain any observables?
Up to a cutoff.
Up to the
Yes. Yes. You mean you must set up a cutoff in the moment and study all the correlator up to this moment.
But for instance, in your two-matrix model, there is AD.
Yes. Yes. You can study. You can bootstrap everything. Maybe it vanish. No, it doesn't. Yeah, a lot of operators, they simply vanish due to the symmetry of them. Okay, let's begin with a toy model for some pedagogical reasons. But this model has a two-particle, this is just a quantum mechanics model. There is no matrix and there is no logic. But this model is interesting by itself due to different reasons. I'm not going to give a historical review of this model, but it is related to several types. And initially, you may get a naive conjecture that this model might be gapless, that is, it has mathless excitation because you see that the x-axis and the y-axis here some flat direction, but you think the particle may run to infinity without encountering any potential. But more detailed study shows that this is not true. This is a well-defined eigenspectrum. Yes. So let's show how the bootstrap works for this model. So where do we begin? We begin with the quantum equation model that is H-commutator with O here for any random operator O. And also the second one is the definition of the eigenspace. That is H with O or any O with H is equal to E O with Z. Together with the word identity, that is, we assume this theory has some global symmetry. Indeed, it has. We have a Z2 times Z2 symmetry in this level. And this quantity basically means that something like X expectation equals 0 to the parity condition, because the potential is A2 invariant. Okay, over here, we can examine some polynomials in the Px, Py, X, and Y. It runs through everything, but you see all the conditions, they are linear. So imposing it on the equation 50, it is equivalent to just imposing it on the monomials of this Px, Py, X, and Y. So what we will get?
Sorry, what is OG?
OG is action of the global symmetry on the operator O. This is a word identity. So OG here, so if suppose it is X, here the OG is minus X. So X excitation equals minus X excitation. So the X expectation is 0. Yeah. Okay, and But if you write down all these equations, you may think you already know everything, but that's not true, because you will find most of the variables, they are determined by a smaller set of sub-variables or free variables. And to determine these free variables, we need to use the positivity condition. That is, we notice that for any random operator, we have such a positivity. And by the definition of the semi-definiteness of the matrix, we have the finally positivity, which actually it is pretty transparent. So here we do the operator, you can see my cursor. Okay. Yeah, here we do the same operator expansion, and we will get matrix. So the claim is that this matrix of operators, it is positive semi-definite. And well, so we have already gathered enough information, and we can solve this model. So you remember that before we have an equation for the eigenstate, that HO equals EO. So the result is that not for every E, this model is feasible. For some E, you will find under distant range, there is no feasible value of the correlator at all. Only on some small tiny islands, you find some feasible energy value. And each of these islands in principle is correspond to a eigenvalue of the Hamiltonian. And here there is a peninsula. When you are increasing the cutoff of the Bootstrap, the peninsula will shrink into a discrete island. That's the general picture. And in each island, you see the x square, for example, it is bounded very precisely by a upper bound and lower bound. What's more, we also have the ground state positivity. That is, if your target is a ground state, you have additional positivity. So this is equation 18. It turns out that this positivity is extremely powerful. It increases the speed of convergence a lot. Well, how to understand it? I don't want to give a rigorous proof of this condition on the ground state, but it is very straightforward. That is, the ground state is defined by that you perturb your ground state with any operator, then the energy expectation must go up. Yes, that's stimulate this condition, and then you massage it, you will get equation. So we can also apply the equation 18 that is the ground state positivity to this simple toy model. And we will get that as we increase the Bootstrap cutoff, of course, the higher excitations, they are all killed by the ground state positivity because they are not great. And we only get one island for the ground state. That is, we are increasing the cutoff with this peninsula and a huge island and a small island. But this cutoff is very low, something like you just consider all the correlators up to something like x to the 8, then it is enough to get this tiny island. And also, this is the same island that is a ground state with and without ground state positivity. I'm not assuming the others they are the same, just with and without ground state positivity, you see that our island or our numerical result, it is much better with the ground state positivity. Okay, another toy model, because we have the preparation, will be faster. But I assume all of you already know this model is a simple one matrix model, one matrix quantum mechanics in the larger limit. Yes. And this model, I mean, in the singlet sector, it is gauge singlet sector, it is exactly solvable. And we just want to use Bootstrap to revisit it because we know it is analytically solvable. We know where exactly the solution is. So here again, we have the equation that is HO equals 0. And we also have the gauge condition that is the G is the generator of S1 gauge condition. And yeah, we are just starting from these two equations. And there are also equations of the cyclicity of the tree, which is also non-trivial and could be nonlinear actually. So what is the result of the equation? Well, it's not possible to do it in real time, the solution, but I just tell you the result is that the result is any single trace composed of p and x. If you try to solve this equation, you will find finally they are determined by the polynomial of the x moment. Yes, polynomial of x moment up to some point. That's the solution of the equation. But this moment of the x moment by itself, they are not determined at all by the loop equation. And you need the help of positivity. That's where it comes in. Okay, the last one is the finite temperature positivity. I will not go into this topic here, so I will. Okay, this is allowed region. Lambda equals 2. What does it mean? It is you have two operators in your mind. That is x and p. You already have some island here. And the curve here is the exact value, which you know is analytical. You increase the lambda, that is 3, and you have a much smaller island here. So you come to the corner here, where the exact value locates also at the boundary of the island. And this story can be increased. And at lambda equals 4, you already have something like a 5 digits and this exact value you locate at one corner of the island. And this is extremely tiny STP problem, that is, you are supposed to generate the whole plot in each. Okay, so we are prepared, and let's look at a more challenging model, that is a BFSS model.
Question.
Yes.
You're only solving for the ground state of that model?
Yes.
So what do you do with the excited states?
Yeah, excited states you can scan over the E in principle, but the upper bound and the lower bound doesn't work because there are really a lot of states, really a lot of excited states, and this model in the larger limit it is gapless actually. I will show you some plots in the end. Yeah. Actually, I prepared such a plot.
Only one technical question. I'm confused. What do you mean by xij? I mean, the I and j take different values.
You mean this equation?
So xi is a matrix.
Yes.
And what is xij?
Xij. Oh, it is a matrix element. Matrix element.
You need one more label. I mean, a matrix has two indices,
Yeah.
and then each of
Oh,
them.
sorry. Then it is xipj because delta, not x provided.
Oh, I see.
Sorry, I'm going to say let me be more precise here. So the condition is xij I p kl j equals I delta ij delta ak delta I. Yeah.
The fact that the exact solution stabilizes near the boundary of this island, is that anything that you expect or is it weird?
Yeah, there is some soft argument to claim that somehow the interesting point or your exact result, they are always located at some boundary or some kinks of allowed island. But I must say they are just wrong. You couldn't take it to here. Yeah, but it happens a lot. Okay, yeah, this model it has some supersymmetry as most of you know. So and fermionic things. So this is quite challenging. And let's gather all what we have. That is equality. We have the equation of motion, the supercharged equation that is mutator with n operator equals 0, and you have the cyclicity condition. Actually, 32. I am talking about cyclicity. That is, you remove the left mode to the latter flow, and also the gauge condition. That is gauge in the condition 35. And you also have the positivity condition, O dash O larger than 0, and also you are aiming at the ground state. So it will be whatever H commutator is over because larger than 0. And a more detailed study showing that since there is supersymmetry, actually equation 38 and 44, they are redundant. How to understand it? Well, you should understand it somehow as H commutator is the square root of the supercharged commutator. So that 39 you are just getting it by the doing the 39 the supercharged equation part, and also the ground state property. This is quite a surprising thought. Okay, so let's talk about the variables. This is a supersymmetric model, so even the variables are a bit tricky, not as straightforward as the previous case. They are just some monomial. Here, since we assume the ground state we have all the relativities and supersymmetry, actually the interesting variable or the independent variable, they are written in this way, that is some tensor structure combined with some invariant tensor. What is invariant tensor? For our situation, it's some gamma matrix, delta, and epsilon. Sorry, epsilon is not an invariant. No, epsilon is an invariant. Yes, epsilon is an invariant. Yes. So, and it turns out that it is not as straightforward as you think, because this kind of stuff, it has some non-trivial relations between this invariant and fully classifying it. They are very challenging. So you need to use field identity or the generalized field identity multiple times to find some linear basis, which could be your variable. Okay, so the equation, how it will look like. It will look like, yeah, this. So here, by this I mean some variable, and you should think of this whole quantity of variable. Yeah, so this will be how the equation looks like. And here we introduce some hierarchy in all the variables to organize it, so that basically a variable you can count here x, p, and psi. So we give them a level that is nx plus. Sorry, there is a table here. This should be 2, not 3, and plus half of the n psi. So what's the benefit here is that you are picking the supercharged equation of the variable. You are guaranteed to get the plus half, the level just plus half. So it is no, and it is easier to actually put a truncation here. So for example, we say level 8, we have all the operators, let's say x to the 8th or p to the 4th, something like that. Okay, this is the number of variables, just for your information. Up to level 9, we have something like 12,000 variables, like what I introduced. But you can solve the relations between them and define that finally they are just 150 independent variable, 149. And these variables, we need to determine them by the positivity condition. Yeah, this is an example of positivity. Due to some group theoretical reason, the operators in different eras, they are just orthogonal to each other by the group theoretical reason. So here, I'm showing you that with singlet for the scalar representation, we have higher representation. Yeah, this is just an example how it looks like. Okay, how the numerical results looks like so far in the last paper. So the numerical result is that we don't get island so far. We get some peninsula that is shrinking. So here there are different levels, almost 4, 5, 6, 7, 8, 9, and you will find the peninsula is shrinking, and this is at the kink there is something happening. And indeed, we can carry some color results with the error bars with some color results somewhere around 4. Yes. So that's the main result we get from the last paper of the BFSS Bootstrap. Here are some data that is, we extract the Montel result from different resource and the Bootstrap result. The larger, the lower bounds, they are simply get by the taking the G here. So I really the value of the G because it tells you what is the lower bound for the prefix in the Bootstrap method. Okay, so till now the efficiency of the method is very efficient. That is to say, up to level 9 for the whole plot, that is, you have something like 30 points, actually 60 points, 30 for the upper bound, 30 for the lower bound. It takes less than 1 hour to generate it. So there is still a lot of potential for this method. But the challenging thing is algebraic side. That is, you have too many variables, too many field identities to deal with. So we stop at level 9. And our main, we were wondering whether in a much higher level, suppose we estimate the potential of the modern computer or something like the first we can go in our method is something like level 50, something like that. So should we go that far, or will it shrink to a tight island, or it just give us a converging lower bound? That's the main challenge.
So you're saying you estimate that you can get up to?
In principle, the limit of the modern computer is 15 or
15 or 16?
Yes, so it's much farther than level 9 still. So that's why we start this bosonic matrix model. Yeah, it is the upcoming result. So this model is, I assume, is also well known, and they are interesting in different aspects. Especially here, at least in this talk, I will just focus on the D equals 2 case, which is simply a 2 matrix form. Yeah, so the Hamiltonian, you can use Z and Z bar variable, and the Hamiltonian is in the equation 52. Because in this model, it has the O2 symmetry, which is much easier than the SO9 symmetry. And you don't have the annoying field identity to deal with. So this model, we can push it to the almost to the limit where we can go. It is interesting. But before going to the limit, let's we do a quick math. That is some analytic form, lowest level analytic form. Equation 53 and 54. You just consider two operators, x and p. You will get the following 66 analytic form. This form is actually a position. It's not an element.
And D here is?
D here is the number of, here D equals 2. But in general, this is true for any D. Yeah. This is a number of SOD symmetry or OD symmetry. Okay. I will not stay this topic too far, but let's look at the result. The result is the orange line. What is the orange line? They are just the analytical result I just showed you. They are. It is surprising that at the level 6 and the level 8, we have the same upper bound and the lower bound. They are not improving. At level 10, that is, you are considering something like Z to the 5, Z bar to the 5. This is one of the low term. You get some island. This is for the mathematical model, so that you are continuing the O2 model, but you are setting the math equals to 0, which is closer, makes you closer to the. So this level 10 island, this is already an island. And then you increase to get the level 12 island, which is much smaller than the level 10. And you keep increasing, this is the level 14 island, which is not transparent here, but somehow indicate this here. And here you have something like 5 digits result. And for m squared equals 1, this is a massive situation. The convergence is much better. So we didn't go to level 14, but we stopped at level 5. Oh, sorry, level 12. And even at level 12, we have very good result that is we have island something more 60. This is m squared equals 1 result.
And m was the m squared was the coefficient of the
Yes.
quadratic term.
Yes.
Okay.
So mathless converge much slower than the massive situation, which is somehow expected. Okay. So here is some benchmark. So in most of the situations, since this is a quite easy model, people always use it as some kind of benchmark. So you compare it to an Hikaru result, and it seems, well, this means that just for maybe this looks very simple for you, but this might be confusing for you because, for example, the Hikaru result here, it means yeah, this is what here is what really means. If you just in case you got confused. So actually, this is very clear that the Hikaru result here underestimated the error part in the larger limit. It is underestimated by a factor of 3 or 5. And here there is the result. This is the best result we get from level 14 and level 12 from the Bootstrap. They are rigorous upper bound and lower bound, so that there is no chance that the real values are outside of this one.
Sorry, what is this model?
Yes.
What did you use to get this result? What model?
What model? Just the O2 model that is.
It's not here.
Yes. Yeah. Here we are talking about much simpler photonic BFSS. You can call it, because we want to understand how the Bootstrap works. Because you remember that in BFSS we go to level 9, and here the island only appear at level 10. Initially it is a peninsula, only up to some much higher level, you say island. We are doing this study try to understand the behavior of Bootstrap so that we have an idea what will happen at higher level for BFSS, trying to motivate try to keep doing the BFSS.
For this model, there are also other results that are maybe more precise than Hikaru. So you compare those with minimization direct.
You mean your paper?
Rodriguez has it.
I think it's not exactly the same model, but we can discuss it. Yeah.
No, he studies the
I'm aware of. I should be aware of the paper you are talking about, but I thought it is not the same model. But we can
commutator models there. There's not much variety of models.
Okay, we can talk about
it.
And he studied both for m equals 0 and non-zero, so that's the only choice you have.
2 matrices.
Yeah.
Okay. Yeah, sure, we should compare it then. Okay. So let me finally. Okay, thank you for having enough time. So let me talk about one of the main challenge of this project. Because for the second project, that the photonic BFSS, we use some arbitrary precision solve. And there is some built-in numerical instability in this STP problem, or the optimization theory, which corresponds to the, you should call it the slab direction in the potential constant. And this is actually due to some systematic reason. For example, maybe many of us you know that BFSS model, some of the moment, higher moment, they are diverging by themselves. They are not really and we are not aware of any systematic way to get rid of this numerical instability. So we use some arbitrary precision solver, something like several hundred digit numbers to try to keep this numerical instability. But in principle, I think there could be a better idea where the numerical instability appears. This is from the physics side. Yeah, for the numerics, yeah, I don't think there is any easy way. And the efficiency, how fast is it? Yeah, the BFSS, the plot, the main challenge is on the field identity side. For the Bootstrap, it takes pretty decent time. That is just 1 hour, you get the whole plot. And the O2 mathless plot, we push it the hardest. That is, it is level 40. So it's the whole plot consists of something like 100 points. It takes around 1. And the O2 massive plot, we just go to level 12. So it's pretty cheap and it should be finished in 1 hour. That is a whole plot, something like 30 times of maximization or minimization. Okay, finally, I will talk about prospects. The first prospect is maybe I still believe that the numerical instability is hidden our core understanding of the flat direction. That is, you know which operator is unbounded, then you can systematically get rid of them. And for the BFSS model, we can push it much farther. And the second thing I want to say is that inspired by the Bobonic BFSS model or just the BFSS model with Integer, we somehow convinced or we tend to believe that at level 10 there should be an upper bound period. And after that, it is shrinking very fast. So this is quite promising. The third aspect is the other system with fine problems. For example, the Yang theory with Hikaru or the XACT model. Yeah, so because BFSS is a well-known model that has some fine problems, and this seems it works well. At least there is no disaster happening. So we are wondering whether for other models. And finally, there's some more further away topics, with finite temperature, for example. I mentioned there is some dedicated positivity for finite temperature, not only for zero temperature. And finite temperature could also be very easy. So that we hope one day we can make it work. Currently, there are some results, but most of them they are unfixed model. And this is the gate model for finite temperature, field model that we are considering. And this problem might secretly related with one or and finally, I want to talk about S matrix is one of the most challenging things in Bootstrap to study. And it's actually, you are always studying some normalized state, but S matrix there are some asymptotic states that is by themselves they are not normalized. It seems this is very challenging, but at least for BFSS model, if you can bootstrap the S matrix here, this is some direct physics result that you can get some information on the box. Okay, that's all. Thanks for your attention.
Hopefully he can you hear now?
Okay.
Can you hear us?
Okay, so and if we take Cn, this doesn't work. So if we take Cn as V, then A mu and psi are just n by n matrices. And on the other hand, if we take the function space of Rd as V, then mu and psi are bilocal field. So mu, how can I remove this one? Okay. I think this equation is quite important. Yeah, so, okay. So the matrix of element of a mu is x, bra, a mu, and y. So we have a sort of bilocal field. And same thing for psi. But of course, this is just a matter of taking basis. So matrices and bilocal fields are same thing.
Sorry, they can't hear online, and I'm not sure what is wrong. Oh, they can hear, but they cannot see the blackboard now. Okay.
It's okay.
I think
Yes, Marco. Yes. So, yeah. So okay. So in terms of this representation, okay. So coordinate representation, the action of the 2D matrix model is written like this. We have bilocal field mu xy and mu yz and mu zw and mu w x. And here x and mu are interchanged. So this is a commutator school. And also this one comes from K. The point is, this expression is invariant under the volume preserving diffeomorphism on Rd, because we have just integration over x. So if we regard mu xy as biscalar field, and then this is invariant under volume preserving diffeom. So in this sense, volume preserving diffeom emerges automatically from 2D map. So probably the volume preserving diffeom is sufficient for general relativity to emerge. And I'm going to explain how this happens. So it is natural to expect that the low energy effective theory of this action is a field theory involving gravity. And we can view this action as a pre-geometric theory, that is a theory that when a certain background is introduced, becomes the ordinary field theory on curved space. So let's consider commuting background. So in the case of CN, this is just matrix interpretation. One of the simplest classical solution is given by the diagonal matrix. So here a mu for mu1 from 1 to d, we have diagonal matrices. So P mu ij is ij element. It's delta ij multiplied by some number, P I. And for mu d plus 1 to 10, we take z. And for psi, we take z. And the well-known weighted reduced model means, suppose P mu I distribute uniformly in Rd. So we regard P mu I as n points in Rd. And suppose those n points distribute uniformly. And also we fix a mu I, the diagonal degree of freedom for a mu and psi by hand. So this is called quench. And if we take the ordinary Gaussian limit, then the theory is equivalent to d-dimensional Gaussian Young mirrors. So this is well known as quenching reduced model. So the corresponding solution in this representation, we call it coordinate representation. So let's see what happens here in this representation. So using the momentum representation, that is just a Fourier transform x, we introduce the identification. So I in Cn, so this has momentum Ki. So we make a correspondence between I and K called Ki in this function space. This is momentum representation. Then the diagonal solution, this is our diagonal solution. ij element is py delta j, and ij element of size 0 becomes like this. So the kk prime element of a mu becomes delta function. Corresponding to this, we have delta function. And we regard a uniform distribution. So this becomes just k mu. So if we consider non-uniform distribution instead of k mu, we have any function k mu. So in this way, we can always interpret diagonal configuration to this special configuration. And then we convert it to momentum or coordinate representation. So by introducing x mu and p mu as the ordinary quantum mechanics, so the commutator is the ordinary one, we can express such a mu is just p mu for mu equal 1 to d, and 0 for d plus 1 to 10. And psi 0 is 0. So in terms of coordinate representation, we just sandwich this. So if we apply x from this, we have a derivative. So the coordinate representation of this is just a derivative of delta function. So this is for mu 1 to d and 0 to d plus 1 to 10. And the xx prime component of psi 0 is 0. So in this sense, we can regard a mu 0 as flat spacetime bubble. And actually, commutator with a mu 0 is the derivative with respect to the center of mass coordinate of the bilocal. In fact, if we consider commutator between such a mu and some operator phi, and if we take x prime component, so the p mu phi is nothing but minus I delta x mu. And phi p mu is minus of delta x prime mu. So this one is equal to derivative with respect to the center of mass coordinate. Here, capital X is just an average of x and x prime, and xi is a relative coordinate, xi minus x minus x. So in this sense, we can regard such background in 0 as a flat space background of the pre-geometric action. So as I said, if the diagonal elements of a mu are distributed uniformly in Rd, and if we consider only planar diagram, then the Yang-Mills type matrix model is equivalent to D-dimensional field theory. This is a statement of Quench's reduced. Actually, some years ago, almost 40 years. Yeah, more than 40 years. So Parisi and his people found this relation. So here, this is the correlator for matrix model. MM stands for matrix. So A mu 1 and I1 2 element, and so on, and A mu L and I. Sorry, this is this is IL and I1. So this is the next one is I2, I3 element, and so on. And this one is equal to the field theory correlator. So A tilde is a Fourier transform of the field. And so A tilde mu 1, and instead of I1, I2, we take this momentum, Pi1, I2. So here, the total momentum coming in is P mu I minus P J. So in this way, matrix model is related to field theory. So this is a Parisi's Quench reduced. And in terms of bilocal field, in momentum representation, this means so this one is nothing but this element, K1, K2 matrix element. So if we consider this kind of product, then this one is equal to this. So in particular, if we consider 2-point Green's function, so we have two point of the K1. This is still in momentum representation. So in momentum representation, we consider K1, K1 prime element, and here we have K2, K2 prime. Then this is the matrix. And this is equivalent to this quantity in field theory. So we have so these two must be the same. So delta K1 prime minus 2 and delta K2 prime minus 1. And here we have Fourier transform of the original Young's field. So a tilde, so the total momentum carried by this field is K1 minus prime, and the total momentum carried by this field is K2 minus. So this is the relation. So we want to see what happens in coordinate representation. So we consider this 2-point grid function in coordinate representation, x1 and x1 prime, x2 and x2 prime. So this is nothing but the Fourier transform of this expression. So we have I x1 k1 for this minus x1 prime k1 prime and x2 k2 minus x2 prime. And we have this expression. And then because of this delta function, the integration for k1 prime is and k2 prime is easy. We just replace k1 prime to k2, k2 prime to k1. So we have this expression from this exponential. And here we have k1 minus k2 and k2 minus k2. So this is a relative. So K1, so if we change variable from K1, K2 to K1 minus K2 and K1 plus K2, we can easily check. From K1 plus K2, we have a delta function for Z1 and Z2. So if we shift K1 and K2 simultaneously, we have coefficient X1 minus X2 prime plus X2 minus X1 prime. But this is nothing but Z1 plus Z2. And then the rest is center mass. So this is nothing but the field theory grid function. And so in this sense, the matrix model in X representation, the 2-point grid function matrix model is the same as grid function for field theory, but with this delta function. So is this okay? So for L-point grid function, we have our x1, mu1, and mu2, and x2, x2 prime, and so on and so forth. And for this kind of L-point grid function, we can easily check that if we consider just planar diagrams and the diagonal elements in momentum space are ignored, then we have this expression. This is Painleve. So we have a more matrix model function equal to field theory function with this. So in short, this means instead of the color factor, in the field theory we have if we consider planar diagram, we have this kind of color factor. And instead of this color factor, we have this delta function for relative coordinate bio function. So this is the summary of this discussion. So if the diagonal element in the momentum representation are ignored and only planar diagrams are considered, the matrix model is equivalent to Largen gauge theory. So, and here, n square degree of freedom of algebraic representation in the gauge theory corresponds to continuous degree of freedom of psi. But the point is, there is no negative state. Because if we, so this, the set of Z, if Z is in the microscopic space, but this set spans a positive definite Hilbert space, because if we introduce this kind of inner product, then this is positive. So in this sense, this is formally with the trace color factor is replaced with the delta function C, and this doesn't introduce any negative state. So at present, the theory is positive. But this one is just for diagonal. We ignore the degree of freedom of diagonal element and we consider planar. So gravitational degree of freedom must arise from the dynamics of diagonal elements and non-planar diagonals. So I want to see indeed this statement is true.
So what do you mean by ignoring the diagonal elements?
Okay, so this is quench. Quench means you don't take the fluctuation into account. You fix the diagonal element to background. And our background is uniform background. So this is quench reduced model. Quench means we fix diagonal elements.
So this allows possibility for other distributions,
Mhm.
except uniform. You can use some other distribution, no?
Oh, yes, yeah, this is a very good point, and I'll come back to this program. And to consider non-uniform distribution corresponds to introduce background to higher spin fields. Yeah, thank you very much. This is a very good point. So before that, beyond going into detail, I would like to mention about Hikaru and the biological. And this is quite mysterious for us, but for some reason that I don't know, Hikaru did not like denormalization theory. And instead, he tried to understand Hadron, at that time, Hadron meant something. So he tried to understand Hadron by extended fundamental objects. That is the local theory. And starting in 1950, he tried many kinds of non-local fields. So the first one is bilocal field, and he considered tetralocal field. And then, finally, he considered elementary domain. So this is what Hikaru did. And so this is the first paper appeared in physical review 1950. So this is okay, and m squared and lambda squared just constant.
What did he mean by elementary domain?
Oh yeah, this is so okay. It's not very clear, but so it's something like a small D3 brain. So yeah, so
What small?
D3 brains. Yeah, is that okay? So around each space-time point, you have a brain. So in some sense, it looks like.
So inside here is a bilocal field.
Pardon me?
Inside here is
Yeah.
a bilocal field.
This file.
Yeah.
This file.
Yes.
Yeah. So okay. So x and z, center of mass and relative coordinates. Okay. So this is essentially bilocal. Okay. The x is the center of mass coordinate and z is the relative. And the equation motion is for center of mass coordinate we have the ordinary triangle. But m square lambda square are constant. So we have another equation, xi square equal to lambda square.
Do you happen to know whether Nambu was aware? I mean, probably he was aware of it.
Okay, yeah, so yeah.
Because I found once by Nambu some papers which are not so far away.
Right. Yeah, you're right. So at that time, many people from power, and some people failed, and they are too faithful to power. And actually, I found one of the name on the visitors list.
Yes, they have that.
Yes, yeah. So Professor Katayama is one.
Katayama was here as a scholar and postdoc here.
Yeah.
Schroeder, probably Schroeder. I think he was between Schroeder or it could have been Heitler.
So, okay, so and then he introduced this kind of construction. And this is something T joint, right? Right here, so close to David's talk, and this is Xi, and then this is P. So this is with that. So I didn't transfer. Lecture at Kyoto University. I think you can see. And Hikaru seemed to try many possibilities of extend the object, but some are not sufficient. So at any rate, the matrix model in coordinate representation is nothing but the binomial. And one of the nice things about the approach from the matrix model that we are taking here is that it has manifest invariance under volume preserving homomorphism before introducing power. And thanks to this, gravity is natural. This is what I want to discuss. So, before that, let's consider effects of non-planar diagrams. So this is a typical non-planar diagram. So we have 4 matrices here, and they are connected by propagator. And the propagator comes from the background, as we have seen. So this gives so delta mu and mu, and exponential k is the momentum of this loop. The k prime is momentum of this loop. So at each point we have this Fourier transform k multiplied by xy minus x1 minus x1, right? And k prime multiplied by x2 minus x2. And this propagator is, as we have seen, just an ordinary expression for dimension. So we have 1 over k minus k. So after integrating over k and k prime, we get this kind of expression. And again, we have this delta function, delta xi y. Delta look is from the beginning, and we have some non-trivial xi coming from this. So the general non-planar diagrams give complex mixtures of the relative and center of mass coordinates. So if we consider just planar diagram, we have this part is just function x. So this is the total system for planar diagram is equivalent to gauge theory. But if we consider non-planar diagram, we have more complicated mixing between relative coordinate and center mass coordinate. So this is no longer equivalent to gauge theory. And also the infinite degeneracy of the mass spectrum in the bilocal field is resolved by this non-planar diagram. Okay. So here I would like to discuss from those modifications we have granted. So, oh, okay, yeah, okay. Well, should have. Okay. Yeah. So this is the expression. In the matrix model, if we consider just planar diagram, we have this expression. So instead of color factor, we have this delta function. So here we have this one. So color factor for E, for example, okay, I think it's better to consider 2-point range function. 2-point range function is So in the case of gauge theory, we have Kronecker delta for color, trace TATB. So the Yamil theory has n squared degeneracy. Adjoint representation has n squared. So instead of that n squared, we have a continuously infinitely located. For each xi, we have the same space. But if we take the non-planar diagram into account, then this degeneracy is the one. So before analyzing the effect of non-planar diagram, I want to discuss graviton as number of stones. So sometimes it is said that gravitons can be regarded as number of stones. And the argument can be general, but for simplicity, here let's consider the Einstein-Hilbert interaction. So the basic assumption is the action is diffeomorphism invariant. And then the action must be invariant under linear diffeomorphism invariant. Okay. Linear diffeomorphism invariant is nothing but GLD. Okay. So the action for constant G mu nu is we consider constant field configuration J. So if G mu nu is constant means invariant under translation symmetry. So the action for constant G mu nu is GLD invariant. More explicitly, if we consider this transformation, G mu is a constant field configuration, and we apply GLD transformation. And from this fact number one, the action is invariant under this transformation. But the vacuum, or for example, G mu nu equal eta mu nu breaks this GLD to Lorentz group, SOD minus 1. So therefore, we have numbers from boson corresponding to the quotient of this GLD divided by SOD minus 1. So this one is nothing but gravity sigma. So which is nothing but H mu nu in this expression. Usually we take this expression, G mu nu is eta mu nu plus some fluctuation around it. So this one is explained as a number of boson for this symmetric plate from GLD to Lorentz.
Sorry, it's probably completely irrelevant, but the transformation of the metric is not usually the M, the transposed on the left of G, but it doesn't, I mean, cannot matter, but in your formula for G prime, the indices are such that from the left you have the matrix.
Oh, yeah, but the same, right? So if you write this in terms of matrix, M, G, and transpose M.
Yeah, but I thought always on the left is the transpose.
Yeah. So this is okay, right? So mu prime is here, nu prime is here, right? So this is
anyway
belongs to tensor, right? So if we write this as a matrix, mention this is M, G, and transpose. This is what that's right. Yeah.
He's just written these out in terms of BFSS. He has written out all the indices.
Yeah. Okay, so the rest is as usual. Due to the diffeomorphism bias, degree of freedom of a vector field can be eliminated. This is diffeomorphism. So, for example, H0i can be gauged away, and we have only HJ. Then, so this is already okay. So we remove the negative null state, but usually after taking the constraint coming from gauge fixing into account, we have the ordinary graviton, just transpose. So what happened in our case? So to be complete, we formally express the bilocal fields as differential operator of infinite degrees. So instead of considering bilocal field, X are center mass coordinate, and instead of considering function of relative coordinate, we introduce derivative expansion. So we have no derivative. This is a function of X, and function of X and one derivative, and function of X and two derivatives and so on. So at least formally, we can expand function of Xi in this way. And as we have seen, the action is invariant under volume precise defect. So the the action for constant A. Okay, so if those things are constant, so that one is invariant under linear volume preserving differential, and also our 2B matrix model is invariant under SOD minus 1 from the beginning. So the total action is invariant, and so for constant field configuration, the action is invariant under SOD minus 1 plus SLD. Okay, SLD is if we consider linear transformation, volume preserving linear development. So that is nothing. So here, mu is the index for A. So mu transforms as SOD 1 vector, while each mu I transforms as SLD contravariant. So if we take this vacuum A1, so suppose this one has non-zero expectation value like this, and suppose others are zero, then this one breaks of this symmetry to your SO. This one is invariant under SOD minus 1. Therefore, we have non-Boltzmann bosons corresponding to this breaking pattern. Originally, we have this symmetry, and this one is broken to diagonal SOD minus 1. And then, as a group of these so this quotient is isomorphic to SOD. So this is nothing but rank 2 traceless test. So, and also this time the gauge symmetry is volume preserving, which is generated by a divergence-free vector field. Okay? So ordinarily, if your model is generated by vector field, but in this case, volume preserved. So vector field must satisfy. So the remaining degree of freedom after gauge fixing is the same as the ordinary gravity because of traceless we lose 1 degree of freedom, but from gauge symmetry we lose 1 degree of freedom. So this part is the same as the ordinary gravity. And also we have rank 2 unsymmetric test. So therefore, general relativity plus Raman fields appear as a consequence of this volume preservation. However, as we will see, this function also has degree of freedom of dilating in addition to general relativity plus kappa. So, in order to see the pattern precisely, let's consider a simple model. So as we have seen, we can express the bilocal field as a formal power series of differential connectivity. And then the equation motion is a matrix model, it's just Yang style. And if you plug this here, you will have a couple of differential equations for the local fields, these fields, right? A0. And in general, these are complicated equations involving infinitely many fields. They are coupled in a very complicated way. However, the set of differential operators of degree 1 forms a closed real algebra. More precisely, if two operators A and B are of degree 1, so here I say degree 1, but this means degree 0 plus degree 0 plus degree 1. Then the commutator between A and B is also of degree 1. Okay, the point is the commutator between this one and this one, when we take commutator, one of the derivative should hit this function. So one is consumed by this function. So the highest degree of differential operator is just 1. So the commutator between the differential operators of degree 1 is also degree 1. So we don't. I think we don't need this. expression. So therefore, the equation motion gives closed coupled equations. And we can, in this sense, we can restrict the operator of differential operators, or we can restrict the differential operator of degree 1, and also we can drop the degree 0 term. Okay, so if we drop the degree 0 term, we have this expression, and again they form a closed one. So this is nothing but the real algebra of different forms. So here the commutator is very long, D bracket. So we can further restrict the operator to the real algebra of volume preserving. So the real algebra of volume preserving differential is volume preserving differential, but the vector field is divergence free. And in fact, we can easily check that if A and B are such type, then the commutator is again divergence free. We can easily check the divergence of the D bracket if A and B are divergence free. But this is nothing but the fact that a set of volume preserving differentials form a group. So as we have seen, the 2B matrix model in the coordinated representation has volume preserving different values. Therefore, one of the most simplest model is a model in which we assume all the matrices have the form of volume preserving different. And we call it the mean model. And the equation motion is just damage type, and gauge transformation is this one. Here, V is volume divergence free. So yeah, I'll answer Antar's question. So in general, we can introduce a constant background to the higher spin field. So we can introduce a background for higher spin field. And in terms of the momentum definition, such background is expressed as this, K, this, and K squared, and so on and so forth. But here we assume the constant in X. So this is nothing but a function K. So in this sense, to choose non-uniform distribution for diagonal element corresponds to introducing the background for highest. So this is the meaning of highest, the background for the highest. And, I think this is okay. I skipped this part. So we have this matrix representation, and the momentum representation is we replace T to K. So if you have just K, this corresponds to uniform distribution T. So, and actually, for the 2B matrix model, we know the effective action for the diagonal elements A and psi is rather complicated, even in the one loop model, if we keep the diagonal element of psi. And it is possible that a uniform distribution of P mu I gives a minimum of the effective action. But as I said, this need not be uniform. Even if this is not uniform, this means we have background for higher spin field. But still it is okay. So the symmetry, if the symmetry is the Lorentz group, this is still okay. So in this case, the background for higher spin fields are all 0. But so in other words, all the higher spin fields are massive because of the background expectation value of them are 0 or fixed to some value. This means all the higher spin fields are massive. So therefore, it is natural to consider the minimum model as a low energy case. So I want to check the positivity of the minimum. So here I introduce a weak field expansion. So in order to check the positivity of the minimum model, let's consider weak field expansion. So this is our A, and A mu is divert each of A mu. If we have a D vector field, and each of the vector field is divergence free. So we have, and so we expand in mu around delta mu plus mu, and del mu of this one. And then the equation motion becomes like this. So we are concerned weak field expansion. So we have A mu is this, and the A mu is this. And then the commutator, we have this A mu multiplied by A mu minus A mu multiplied by A mu. Right? So this one is A mu, and this one is A mu. But we are considering a weak field C. So this one is already with a C. Okay? So we just keep this part. So we have a contracting with lambda, we have del mu C, del mu also. And then this is so this is nothing but a gauge field for abelian. Basically, if we regard rho as a kind of eternal degree. Of course, rho is not eternal degree of freedom, but the full expression itself is something that is right for now. And then we take next commutator, this one u, and this time we have already order 1, so just the u we have just leaving del mu. So we have this. So this is the equation. So again, this is same as abelian. And the gauge transformation is written like this: the commutator into some divergence free vector field, and then so we have d mu, and we have this and minus a mu and then. So again, in the leading order, we drop this one, and we simply so this one is dropped by so this one we just put this. So we have there. Now again, this is something gauge transformation that you want if we regard lambda as something eternal.
What about concrete solutions of the equations of the minimal model? Have you thought about concrete solutions?
Concrete solution for non-linear case? Yeah, I haven't. Yeah. So this is just for linearized version. Linearized version is trivial. So, but I haven't tried full non-linear version. Yeah, I think it's very interesting. Okay, so we have in the linear level, we have this equation motion, and this one comes from being. We have divergence field, and we have this gauge transformation. So it looks like direction, but the gauge function is again should have this divergence. So using the gauge symmetry, we can fix the gauge to Lorentz gauge, so del mu C mu is there for each number. Then this term drops, and we have this equation motion, and we have this constraint from the beginning, and we have this constraint by gauge fixing. So in this way, we have massless state corresponding to a rank 2 tensor -1. So that is random Kalkuramon until. So this is the same as first. So far so good. I want to discuss the difficulty of the action.
Just to maybe continue, you can expand that to the tens of three and so on. Next order.
Oh, okay, yeah, okay, that's a very good question. So the point is, okay, usually, okay, even if it is good in the linearized level, and if we consider interaction, the symmetry could be broken. But in this case, the point is the volume preserving difference. If A mu and A nu are volume preserving difference, then this is also volume preserving. So divergence-free condition is completely satisfied by this equation. So in this sense, nonlinear term is safe. Yeah, thank you very much. Yeah, this is very important. Okay, so how much time?
Maybe
Yeah, 0?
7. No.
Okay.
7 minutes.
Okay. So equation motion of the minimal model is very simple and seems consistent. However, there is a problem in writing down the action. So in fact, for this differential operator, the action trace in commutator square is not well defined. So this is because if we consider this trace, because of this delta function, that is STP. So the original action is finite if the bilocal fields A mu are smooth function of the excitation, right? The problem arises from the delta function. So the derivative expansion is not very good in this. So derivative expansion is good to examine the structure of equation motion, but to examine the action, derivative expansion. So more generally, the derivative expansion is useful for analyzing equation motion, but it's problematic when considering the action. So we want to regularize UV regularization. So the simplest idea of regularizing trace with some UV cutoff, but this doesn't work. For example, if we regularize a trace like this, we grab some cutoff here, but this definition violates permutation bias. Trace AB is no longer trace B. So then the equation motion is no longer. So this is not good. And another idea is to regularize operators themselves. So we put some cutoff to the operator. Then the permutation invariance is of course satisfied, and the equation motion is of course this type. But one problem with this is that the commutator of the two operators contain higher derivatives. Okay, so if we consider commutator of this one. So this degree 1 differential operator with this regulation. But if we take commutator, we have degree 3. So here we have epsilon. So formally, okay, it looks good in the epsilon 0 limit. This disappears. But if we take trace, okay, so this remains because derivative this is singular when we take epsilon. So in this sense, this term remains if we take trace. So again, we fail to derive the action. That is
Could you not have smeared your delta function?
Yeah. Okay, so smearing delta function is probably equivalent to this idea. This idea. So derivative operator is delta, the derivative of delta function. So here we insert heat panel. So this is essentially smearing delta function by. So the point is we have. So the situation could be described. If we express the Yang-Mills-type matrix model in terms of bilocal field, both the action and equation motion are finite. And expanding the bilocal field as a formal power series of derivatives, the equation motion becomes a series of differential equations for higher speed field. And this equation motion has no divergent coefficient, but the action is no longer a finite function. So the truncation of the formal power series at degree 1 gives a self-consistent equation motion for spin 1 field. This is consistent in that it describes special solution of the full system. However, it is difficult to find a closed form of the action for the spin 1 field. However, this situation is commonly in loop space or more generally in the Schwinger-Dyson equation, as noted by David Factor a long time ago. So I think probably we can find a non-local action that replicates the equation motion. I haven't succeeded yet, but I believe this is true. So, summary. If the emergent spacetime can be described by matrices that fluctuate around diagonal matrices, it is useful to represent the matrices as bilocal fields. And the action of the 2D matrix model in terms of bilocal field can be regarded as a kind of pre-geometric set. And at the pre-geometric level, that is, before considering the emergent background, the theory is variant under the volume preservative. And general relativity arises as a low energy effective theory consisting of non-Boltzmann bosons around the emergent field. So technically, bilocal fields are more tractable than higher speed fields and may help us better understand the dynamics of matrix. So this is all I have to say. Thank you.
So, okay, I'm very happy.
It obviously needs an introduction.
Yes, I'm very happy to be here, maybe third time in DIAS, and to be able to give a talk. I want to talk about explicit solutions of double-commutator equations. And I wrote them in historical order, and it's nowadays called BFSS model. This the IPKT model with a Lorentzian metric. And this can be either considered coming from this with time being 0 or a static solution of this. And I will start with this one. You will hear, okay, I make the remark as appropriate. So in 98, Kornalba and Washington Taylor wrote a paper called Holomorphic Curves from Matrices, and they considered solutions of these equations. For instance, for d equals, so here's the sum, j from 1 to d, and for d equals 4, they considered x1 plus I x2, let's say is w, x3 plus I x4 is z, and then they specifically considered the case where z is w squared. And w is a matrix which is non-zero on the first upper or lower off diagonal, infinite dimensional. And the interesting thing is, although it was a PhD or the major part of the PhD thesis of Kornalba, and who wrote the, I mean, he got a PhD from Princeton University. And Princeton was 100 years ago dominated by Luther, Thaler, Eisenhardt. Very hard words in German. Thaler means something put in there, and Eisen is iron, and Hart is hard. And he did a lot for the mathematics, and he wrote many books on minimal surfaces. And 100 years ago, he found that in 4 dimensions it's very easy to find minimal surfaces, basically all holomorphic functions. You could take anything any function here of that will be classically a minimal surface. And the funny thing about the Konalba-Washington-Taylor paper is, although it is written in Princeton, the whole paper, 40 pages, doesn't mention the word minimal surface. But it's, of course, irrelevant. They considered this, and then they derived the following equation, which I will only comment now for 5 minutes, because you will have a wonderful talk by Andrew Hone. Is he here?
Yes.
Andy, where I have bad eyes. There you are. Okay. Who with collaborators also worked on that. And so I will only briefly mention this. Various reasons why I do that. Because I need it, independent of, not only because Andrew will talk after me, but also because some of the things I say here is slightly related to this. So you find that you can solve these equations if you have the following equation: W dagger W plus Z dagger Z is central. So let's say a constant times the unit matrix. And they considered specifically the case that it's equal to W squared, which is a non-commutative parabolic minimal two-dimensional surface in R4. And they found the following equation: Bn times 1 plus Bn plus 1 plus Bn minus 1 is equal to epsilon times n plus 1. And they did a lot numerical. They couldn't solve it. They saw that this most likely, so the Bn's are the absolute value squared of the non-zero elements of the matrix W. And so they have to be positive or non-negative. And so they speculated already and had numerical evidence that there is a unique positive solution of this. Let's say with B minus 1 equals 0. And then you have B0 as a free parameter, and then all the other ones, B1, B2, B3, are all determined. And semi-classical, you can come up already with a pretty good start, and it's almost, but then the fifth or the sixth gets negative, and they couldn't prove it. They couldn't prove that they speculated that there is unique. And then Arnlind, Konsilich, and me, we tried in 2019. I think I also have the number somewhere here. 1903.10792, called quantum minimal surfaces. And we did some more general things. In particular, we tried to find the quantum version of the Cartesian Euclidean minimal surface. Even there, although one of us famous guy, we actually made not a mistake, but we missed one point. And the main thing I want to talk here, which is not yet published, is actually I found the missing point, and it's quite an interesting point. And I'm claiming that we can solve this in rather general terms, this equation. I mean, I knew this for a while, but I just recently sat down to do it explicitly. Anyway, so we found out many things about this nice equation. And of course, at EHS, there are many experts, many Russians also who know about discrete Painleve equations. In particular, there was a young student, I forgot her name, but it didn't help. I mean, we found out that it's called discrete Painleve 2. Or it can be called like that. But it doesn't help to solve it. No Lux pair. One. Sorry, thanks, Andy. Discrete Painleve 1?
Yeah. 1.
Okay, you see. He will talk a lot about Painleve. And in particular, what Andy will show, together with Clarkson, Anton, I know the Jamai, and Ben Mitchell, the student, they found out that the VNs, that's this paper here, they found out that the VNs satisfy the continuous Painleve 5 equation. And that to go from Vn to Vn plus 1 is a Backlund transformation, which transforms one solution to another. And now, the reason I mentioned it, so what I did in this, I wrote a little, my contribution to this part of the board is minimal. I wrote a small paper. I mean, through the discussion, we said, okay, I leave out many things, the medical things and so on, my state. And so I wrote a little paper called Quantum States for Minimal Surfaces. And the thing I want to mention, because I think it's not uninteresting, is that these are related to Schrödinger problems with interesting potentials. So the VNs all give equations AHN psi n equal minus psi n. So solution of a one-dimensional potential problem with energy minus 1. And each Vn gives a different potential Wn. So it's always minus ds squared plus Wn. This W is not that W. The Wn is a function of S. And W0, so this is Hn. And W0 is minus 2 over 9 S squared. So you get the Hamiltonian minus ds squared minus 2 over 9 S squared. And now the funny thing, so the interesting thing is that there are papers who rate this to Riemann hypothesis about the zeros of the function, zeta function. And that could be interesting because what Giovanni Felder, who basically, I mean, I also got to read a little bit, but most of his work is in April. He's very good. I just, basically, I asked him something and he knew the answer. And he had written papers on random normal matrices. And so that's also interesting that these equations are related to random matrices, which in some sense was always suspected. I always wanted to make some contact for a long time with the Voiculescu's work, but never successful. Anyway, so but the warning is, so all the Vn's, so W1 is something like minus 5 over 36 S squared plus 1 over S. And the W2 minus 2 over 9 S squared plus 2 over S. And then the next W's become more complicated, but they all have these asymptotic behaviors. Now, the warning is, you can factorize this. So I didn't work it out. So in this little paper, I didn't mention that I want this to be in this AN dagger, AN, and then you change the order, and then you go from one state to another, or from one Hamiltonian to another. So you can factorize this. You can factorize it as ds plus 1 over 3s times minus ds plus 1 over 3s. So it's of the form A dagger A. And if it's of the form A dagger A, it should be positive, the operator. That's usually how you show that operators are positive. But you can find the psi 0. So the psi 0 turns out to be K1/6 of S, maybe times square root of S. And it's a normalizable function, falls off at infinity. Integral ds from 0 to infinity is finite. Exponential fall off. No, there is a singularity at 0 because maybe not even that. Anyway, it's fine even at 0, it's integrable. And so something is wrong. And the other thing which is wrong is that this is scale invariant. So if it has a state which satisfies this, you can immediately scale psi n and you have a state which has an even lower energy. So this is not formally self-adjoint, this operator. Because, okay, no time, I want to come to the other things.
So what are the defect indices?
Sorry?
What are the defect indices, 1, 1, or?
I think so, but sorry, the simple answer, I don't know. But I looked, of course, at how it works with these self-joint extensions, and I may memorize, but I don't at the moment memorize the answer. And okay, I could tell a funny story with that related to Europe, but but I asked for help. Anyway, so let's come to these things. And now, before that, I just want to mention what we, or basically maybe Giovanni, found in our joint paper, a relation with orthogonal polynomials. And this was speculated already by Andrew also and Peter Clarkson, who is an expert actually in this. And I thought always it should be related. And the reason I had asked Giovanni is because he had an equation with a former PhD student, Elbau, some time ago, where he worked on this relation to normal matrices, where only the signs are different. And there were lots of papers by Zabrodin, Wigman, Theodorescu, and also other authors on relating these kind of equations to Hill-Shaw, Laplacian growth, and other interesting things. Anyway, so we managed to relate it explicitly to orthogonal this case, and it's actually nicer than the one case worked out by Wigman because the integrals actually converge. And the measure is, so there is you take functions of complex variable, and the scalar product is the integral f of z, g of minus z bar, and then the density is e to the minus a absolute value z squared plus I over 3 z cubed plus z bar. And the relation with to normal matrices is where you don't have an I here. And when you don't have an I, the integrals don't converge. But when you have an I, these actually for polynomials, they're completely fine. I've thought about it, but I didn't want to. Thank you very much. Thanks very much. And so the VNs, so you get orthogonal polynomials here, which satisfy Pn, Pm is delta nm times the normalization constant, and the Vn's are ratios of the Hns. Now the problem is this is not a positive definite scalar product, but it's real for real permission or whatever. So there is a sign, I think it's -1 to n. And then the Hns are positive and the Vn's are up to factor maybe 1 over a squared or a cubed. I don't remember. Hn plus 1 over Hn. H squared, a squared. So, and epsilon, that's of course important, relation of epsilon to a, epsilon is 1 over a. So the epsilon in the original from Alba, Washington, Taylor thing here. Maxime has another view on this. He also wrote with his student King's equation, I think he calls it. And there are some other things related. Anyway, with these identifications, what you have to work out is the integral of the measure, h of a, which is defined as the integral is here dz squared over the whole R2 or the complex plane. And h of a is defined as the integral e to the minus a z squared plus I over 3 z cubed plus z bar cubed. And then you can either directly calculate h, or you find the differential equation, and then I think it's like this. And it's already some time ago. Yeah, it's like that. And then you find out that the h, either by solving this with some normalization or working out directly the integral, you find out that it's e to the a cubed over 6 square root of I over a divided by 3 times Bessel function. And so that's one way. Andy and Peter Clarkson and the 2 other collaborators, they got it from this Painleve 5, which becomes simpler it has Bessel function solutions. And they got the corresponding formula for V0 in terms of Bessel functions from their considerations. Okay, so I started with this now. Now the main this is maybe for this conference the most relevant one, because many of you work on these equations, and I just want to show that it is possible to explicitly solve these equations in some mild generality, and that could be useful. But I first want to, because I have one example and then lots of speculations or so, I do want to comment on this, because there's something I'm very happy about. Explicit membrane solution. So I derived this Goldstone a long time ago, and it was my PhD thesis from we regulated membrane theory. But there was very little known for the 60 years since Dirac paper about explicit solutions of continuous membrane solutions. So Dirac found it, and then everyone who looked at the problem finds this round sphere which contracts, and the radius is an elliptic function. And as a function of time, that's very simple because it reduces to an ODE. But otherwise, so 1962 Dirac, and then I by chance found the solution t squared plus x squared plus y squared minus z squared times t plus z squared equals constant. And it's time-like minimal surfaces, so it's moving membranes with velocity smaller than 1 if the constant c is smaller than 0. So the set of points t, x, y, z in R4 or R31 satisfying this equation describe a minimal surface. Minimal 3 hypersurface. Minimal 3 manifold in R31. That's 1994. But that was for a long time the only other class of explicit solutions. And then recently I found a host of new solutions. And the mathematicians like it. I'm very grateful that Huskin discussed, we discussed sometimes, and he likes it, and somehow. From a mathematical point, it's even more astonishing that you can find explicit solutions. So they are even polynomial. So you always need one specific power, so it's 6 in this case. And in this case, the constant has to be positive. That is maybe 2 years ago, 2022 or so. And the one I want to talk about here is, I called it the fast non-commutative sharp drop. So I first write down the classic solution, and then the classical solution gives an explicit solution of this in terms of representations of SO21. And that's nice. It has some generality, it has some parameters. It is abstractly nice. Harold, who is no longer here, would have been happy because it involves the fuzzy, not torus, fuzzy cylinder. No, yeah, maybe fuzzy cylinder. And it's nice. I mean, if you like, and I will give it. And then finally, I come to this in the last part of the talk. And then I have 2 extras, but time is always the problem. So as a level set, the solution I talk about now looks like this: t squared plus x squared plus y squared minus z squared. It starts out like this. Minus 6c square root of x squared plus y squared, so not polynomial, times e plus z squared plus 3c squared t plus z to the 4th equals 0 and c smaller than 0. Now, when you view this as a time evolution of a two-dimensional surface, it's a sharp, it's a drop. It has a sharp tip, and it zips. It moves very fast, I think, in this direction. And it has two sort of small problems. It has a sharp tip, that's a singularity. And it has one point which moves with the velocity of light. And that means that it's a singular three-manifold because it's not timeline. It has a point where the metric vanishes. And that leads to the fact that usually, so this, Goldstein and I considered this, and we're interested in finite matrices. The general rule is if you have a compact two-dimensional surface and you approximate it, you have finite matrices. And the reason why my solutions will be infinite matrices satisfying this is because of the singularity of the classical surface. And I think actually it's more relevant, the velocity of light, than the sharp tip. The sharp tip actually usually is also interesting, but it has to do with drop of dimension of surfaces. I worked that out in the CD Hikaru, Shimada, Martin Borderman, and who were the other two students? Hoppe. Joachim, of course, my student Joachim. Yeah. And anyway, so it looks like this. You can make a movie. And now, why does it give a solution of that? Well, one way to view, maybe you have to always switch. I stay here.
I am doing that, that's no problem.
Is no problem?
Yeah. You have a blackboard to the left as well.
No, I right here. Right. So we have X view. T R of t and phi cosine theta, R of t phi sine theta, Z of t and phi. This describes an axially symmetric membrane, time-dependent, in 4 dimensions. But you can also describe it in light cone coordinates. And then it looks like this. And just like here, in order to find the surface or the moving membrane, you have to find 2 functions of 2 variables. And in this case, they satisfy the equations r dot r prime plus z dot z prime is 0, and r dot squared plus z dot squared plus r squared r prime squared plus z prime squared is 1. I'm leaving out lots of subtleties having to do with reparameterization and so on. Now, the light cone version, you will see why I talk about it now, has similar equations, namely, so in this light cone version, you want to find 2 functions, big R of tau and mu, and zeta of tau and mu. Zeta is called usually in string literature x minus, and tau is x plus, tau is x0 plus x3 over 2, time plus z over 2. And you see in these equations always you have t plus z, tau enters here. And zeta is t minus z. And you want to find zeta. And just the equations for zeta are zeta prime is r dot r prime, and zeta dot is a half r dot squared plus r squared r prime squared. Now, in these coordinates, it's easy to eliminate zeta. Just the dot of this has to be the prime of that. And you get an equation which is the simplest version of axially symmetric membranes. And my dream is still to solve that theory. And I claim it has a good chance of at least in some sense having strong integrable structures. It's Hamiltonian. It comes from integral r dot squared plus r squared r prime squared d mu. And this is how I found this solution. So this has one simple solution, r square root of 2 mu over tau. So prime is derivative with respect to mu, dot is derivative with respect to tau in light cone coordinates. So you see that the left-hand side gives 1 over tau cubed, the right-hand side gives 1 over tau cubed, and the mu also works.
If you do can you do a holograph transformation and change it to the wave equation?
I tried. It doesn't. I'm thrilled if you manage to do it. I want to solve this.
Yeah.
And I still think it should be possible. But I tried many holograph-related possibilities. Anyway, this is a trivial solution. But the interesting thing is you can add to the nonlinear equation, to the solution of to the nonlinear equation, you can add something. And you can add tau cubed. And epsilon is 4c. This epsilon is not this epsilon. So, and this solution is easy to verify here. And then you calculate zeta from these equations, and zeta is t minus z, and then you find that they satisfy this equation. That's how I found this solution. Now, you write now in light cone, so you have an x, which is r of tau and mu times cosine theta psi, and y is r of tau mu times sine psi, and that's x1, that's x2, and they satisfy the equations xi double dot or xa double dot is Poisson bracket xa with xp with xp, and the constraint xa commutes the sum over a Poisson bracket of xa with xa dot is 0, and the Poisson bracket here is derivative with respect to mu and psi, and dot is derivative with respect to tau. So for this sharp drop moving, you show that classically these equations are true. And then you just replace functions by matrices, and that involves the fuzzy cylinder. And it's the details are actually quite interesting, but I'm worried about the time. So you write the xa, maybe I do a compromise. You write the xa as square root of 2 over tau, that's this factor, times xa bar. And then you find out that the xa bar and then you call x1 bar with x2 bar, you call x0 bar. And then you find out that the x012 bar satisfy SO21. So the Poisson bracket of x alpha bar with x beta bar is epsilon alpha beta gamma x bar gamma, where you raise indices 0, my metric is 1 minus 1 minus 1. And then you replace commuting x bars by operators, big X. And then you need representations of SO21. And it's even more interesting because the x bars have two parts, this part and this part. Oh, sorry. Yeah. Squared. The reason why 3 was stuck in my head is if I take out the square root of 2 over tau, I get the power 3 here. But it's like this, sorry. Anyway, it has two parts, and both parts satisfy the commutation relations of SO21. And it's quite interesting. So anyway, what I'm saying is some progress with classical solutions and an explicit solution of that for d equals 2. So here's always the sum j from 1 to d, which is big spacetime minus 2. And this solution, this non-commutative sharp drop, is 4-dimensional spacetime.
Or infinite matrices.
Infinite matrices. And the reason they are infinite, although the picture is compact, is because of this point moving with the velocity of light. That makes it non-compact.
Can you say anything about the traces of powers of them or anything? Are they finite or?
I don't know. I haven't. Thanks for the question. I will think about it. Now, there is now half a topic that I want to talk about. Unfortunately, then I have to wipe out something here. So there is a host of string solutions. So I'm now coming to this. And I don't know which order. Okay, first the less relevant comment, but also nice or important. There is a host of string solutions which people have not considered. Maybe half. The people always think classical string theory is trivial, but in flat space time. But it's not true. First of all, the singularities, there's a theorem. Every single closed string moving in 2 dimensions, such that it sweeps out a minimal 2 manifold in R21, becomes singular in finite time. I always thought I'm the first. I have a very elementary proof of that, but actually some Russians were earlier. And it was mathematically proven by Gangtian and Nguyen. And they have a mathematical theorem. There is no minimal hypersurface, time-like minimal hypersurface in R21 that has the topology of a cylinder. And with all the mathematical rigor. Now, but there is a loophole to that. All theorems, all no-go theorems, and I'm saying there are the following. T squared is x squared plus sin squared z. Defines a surface in R21, coordinates x, z, and t, or t, x, z. And at t equals 0, yeah, it's a dot. It grows, and it grows, and it grows. And it violates the theorem proving by famous mathematicians and my own pedestrian proof. You wanted to ask a question. And the point is that these are infinite energy solutions. Because if they grow and grow and grow, they have to come somewhere, the energy to grow. And the reason why this undergoes the theorem, of course, the mathematical theorem proven by known mathematicians is correct. But the point is, it's not the time. There are points here which move with the velocity of light. And at that time, the reason the energy of these solutions diverges, why they have infinite energy. And there are infinitely many such solutions. This is just the simplest example, and they have not been considered much in the literature. And I wrote some new type of membrane solutions. And there are also membrane solutions. Now, why this becomes interesting now when we move to the thing. I see some people.
You were going to say why they have the infinite energy.
Yeah.
This is not obvious.
At the point, the energy is. So can you ask me when my official time is over? I love to comment on that, but it takes 4 minutes. Or maybe you don't ask now, but please ask. Well, it's just at the point where they move with velocity of light. That's the point where they can have infinite energy. And if you calculate the integral, if you calculate the energy of these, it diverges because of these 2 points. And now the interesting point is matrices are more clever than continuous functions. So originally, Gaussian and I, we wanted to do membrane theory, and then we thought, this is non-renormalizable, so we had to think of the fuzzy sphere. We found matrices, and then we first did it for the sphere, then 10 years later, people found the fuzzy torus construction, then there was a big puzzle, then we found, and Schlichenmeier, Bordemann, and Mein-Renken proved very nice mathematical proof. It works for any compact two-dimensional surface, the approximation of functions by matrices, and even for some compact Kähler manifolds. But now I lost the thread because of Martin. I wanted to talk. Right. So, but the nice thing about the matrix models is they contain all topologies. And actually, we don't understand what to do, for instance, with the BFSS model, how to get these things. But surely they are all there, and also star product membranes. And as we heard in the talk before, I mean, you have all the infinitely many differential operators. When you, it's a huge area one is covering with these kind of equations. And the funny thing is now, this is work in progress with Giovanni Felder. We can find some solutions of this explicitly and the general construction, but when I try to apply it to this, it doesn't work. So I think it doesn't work because the matrices say, no, I'm infinite energy. You can't do it. Anyway, I come to that. I have only 15 more minutes. So let me come to this. Now, you have seen many derivations. My derivation was the following. I considered, so usually you take square root of g, number action. And then you get 1 over square root of g, the alpha squared of g alpha beta, d beta x. Now, the Schild action is integral g. And then you get the equation d alpha g d alpha beta, d beta. So not square root of g but z. And maybe some vector here. But and this vector is only there to make it invariant, this operator. And this is not fully invariant anyway, so it's not so important to include the vector. And actually, it's an advantage of this that you can also have vanishing. So now, this object, inverse of a matrix times determinant, is polynomial in the matrix elements. So this can be written, I noticed this in this paper, FTH, that you can write these equations in Nambu bracket form. X mu 1, X mu 2, X mu m plus 1, X mu 2, X, yeah. 0, 0, 1, m, X mu 1, X mu 2, X mu m equals 0. And so for an n-dimensional extended object, and for the string, you get x mu, x mu, x mu. Now, I considered this without fermions, and it was just one page in the paper, so I'm not. But it was before the iPad. So, and the reason I found this interesting, and that's also something which somehow I find it significant. There was this paper by Feldenhagen, Doppeldicher, and Roberts on algebraic formulation. How does space-time, how could the quantum theory of gravity look like? And So I just thought, well, this of course looks like you just replace functions by matrices, because I knew how it works in this case. So I considered this and said, well, this is interesting to think of this. And because of the paper of Friedman, I should do Spacetime or whatever. And I was looking in that paper which I wrote actually for the generalization of the what is the quantum version of the Nambu bracket, and I couldn't find it. Now, the catch is now the reason I do this is because the constancy of G plays a big role. And I looked up the new paper. I mean, the derivation you had. You do a Polyakov version. I did just simply this. I took this and I derived this. Now, the statement, why are they equivalent? So this is a consequence of these equations, is that G is constant. So if any x which satisfies this equation of motion necessarily leads to the fact that the metric G is constant. This is a simple proof. You multiply this with d gamma x mu, and you sum over mu, and you prove that d gamma of G is 0. So every solution of this has the property that G is constant. Now, this equation is fully diffeomorphism invariant, so you can choose G to be constant. And that's how I would prove that they are equivalent. Now, when you now I come to my main point about how to solve this. You have to make sure if you take string solutions and you say they solve this, you have to make sure that you have a parameterization where the metric is constant. Otherwise, it doesn't work. So I give now one example. And the example is, what's the simple string solution? X mu of p and phi, it's just a circle which shrinks. So t, cosine phi, cosine p sine phi. It's just a circle which, when t goes on, it has a certain radius 1 maximally, and it shrinks, and then it becomes a point, and then it vibrates. That's the simple string solution. Rotationally symmetric. Now, the question is, and that I want to show more or less explicitly, what is the solution of the IKKT equation, which corresponds to this simple solution? And I always thought it's a scandal. I mean, we have these equations for a long time, but and there are some, you put constants and x and p and so, but we don't have non-trivial solutions. So finally, I managed, and I can see how, in general, to solve these. And I thought at this conference it's the right place for you to mention it. Although the paper is not really great. So how do you do it? This does not solve this. But you have to reparameterize. And you have to choose. So if you calculate the metric of this, you find it's cosine squared t times 1 minus 1. So it's conformally flat, but it has this factor. So you have to reparameterize t to make g constant. And so you solve, you find a new variable d tilde, which satisfies, and this works in general. You take a string solution, we know all string solutions. You make sure you reparameterize your known string solution in new variables, t tilde phi tilde, such that in the t tilde phi tilde variables, the metric is constant. G tilde is constant. And then you get x mu, the operator which satisfies this equation, by x mu tilde of t and phi, where t and phi are the quantization of t tilde and phi tilde. So t is phi. And this works pretty good for any exam. Now, of course, you cannot explicitly, it's only a semi-classical. But in some cases, you can go beyond the semi-classical. And for instance, in this simple case, but I think somewhat, I mean, not absolutely explicit for the absolutely general case, but you can do more than maybe one would have thought. So I solved this. Unfortunately, I can find t tilde as a function of t, but what I need is t as a function of t tilde. So t tilde is something like a half t plus a half sine 2. So t tilde as a function of t is explicit. Inversion, no. But it's good enough. I mean, you know that dt by dt tilde is 1 over cosine. So you can prove that if you think of this as a function of t tilde and phi tilde, it has constant metric. And then you plug in these operators, and one can get solutions, infinite matrices or operators satisfying this. And in that course, I noticed the one point which was missing in the paper with Joachim and Maxime. When we try to quantize the cutting reed, which is the only axisymmetric minimal surface in R3, just like this is the only axisymmetric surface in R21, we found somehow there was too much freedom in our solution. And to eliminate that freedom, I found out now, is related to this making the metric constant, and it works beautifully. You can explicitly find out these matrices, x0, x1, and x2, explicit. And time is not enough, because I want to mention 2 more things. Now, this solution is cosh. I always forget cosh. Oh, that's bad that I forgot. Well, I have to look it up. I think it goes like this: cosh b, sinch d, and the last one is u. Does that work? Or maybe sinch. Sorry. Embarrassing, but I'm getting old. Now losing valuable time. Sinch.
Well, I looked like called the first better comment.
T squared.
Called the
Maybe it's correct. But
there is a hyperbolic cosine of v.
yeah, Finch. I hate it. That's the only good thing was I always remember cinches. So does that work? The squared of this, yeah, sorry, it has to be cinched. Now, this is the cousin of this solution. This is S1, this is SO1, 1 invariant. The other one is SO2 invariant. And you can now try the same thing. I reparameterize U as a function of U tilde. But the key is this. And there always has to be sometimes the topology of the thing. Now it's very bad that I wipe this out. Essentially, you don't have to change from one version to the other. And so, yeah. So it seems it's very weird. You can do the same thing I said there. You can do here, but then we have an argument, Giovanni and I, that there is no solution to the equation. And it's quite weird, but I don't have time to go through that. Now, the last 5 minutes.
7 minutes.
7 minutes, okay. At my heart, I asked this, I talked about it at CERN, and Denjo said, oh, he knows how to do it, but I still haven't done it. So I want to know the answer. So it's these equations. So as you see, I'm very pedestrian, and my thought, apart from this one idea, which I also think it's a pity if it gets lost, in 2010 or 11, I found a dynamical symmetry for extended objects. And I think that there is a chance that one can get the spectrum of extended objects, relativistic invariant theories, just like like Pauli solves the hydrogen atom. And it's intimately related to Lorentz invariance. It's very interesting. And there are 5 papers like 2010. One is called Fundamental Aspects or Fundamental Properties of Aspects, I think, of membrane theory. And apart from that, there I think one algebra, if you want to show integrability or prove it, I think there is a chance. Now, apart from that, the only way I can make progress is to understand the classical theory and then find maybe some integrable structures and then quantize it. So the simplest non-trivial theory is exclu symmetric membranes. And that's why I said this looks pretty nice, but I know I don't have a Lux pair. I don't have infinitely many conserved quantities. Now, I have a question here, and then already knows the question. This formulation, which is the obvious, we are looking here, we see an axially symmetric membrane moving in front of our eyes, and we describe it by these 2 functions r and z of t and phi. Now, I can write those equations in the following form. Z dot is some function of r dot, and r prime, which I denote by f of r with square brackets. And then that prime is minus r dot r prime over f. And f is pretty complicated. So if you eliminate one of the 2 functions you want to find in the geometrically more simple case, you take the prime of this and the dot of that, you get a second order equation for r. And but f is pretty complicated. F squared is a half 1 minus r squared minus r squared r prime squared. This I call p, plus minus square root of p squared minus q squared, where q is r dot r prime. Now, they satisfy some nice equation, namely f plus times f minus is q. So suppose I take one of them here, 1 over f, I can replace by minus f tilde over r. And the equation I get for r is, and then I ask my question. So the equation of motion I get is r double dot minus r squared r double dash minus 1 over r prime squared plus 1 over r minus plus square root of p squared minus q squared equals 0. So it's some second order equation for r. And my question is this Lagrange? And then you said, when I talked about this at CERN, there is a way to find out. It's pretty simple to see, but I still don't know. And I have many interesting properties of this version, in particular related to a zero curvature condition, something moving, but I still want to know. That's one question. And the second question is, everywhere in this game, when you look at axisymmetric membranes, you find pairs of functions which are related. And it's like Cauchy-Riemann equations. So Z is V prime, and that prime is V dot over R squared. Now, if the 1 over R squared was not there, this would be the Lorentzian version of Cauchy-Riemann. Ux is Vy and Uy is minus Vx. And then, so Z satisfies the equation that double dot is R squared Z prime prime. So without that R squared, it's just a wave equation. And the whole point of these axisymmetric membranes is this R squared. This factor is the problem, and this factor. But so the second question is, what is the geometric meaning of V? And everywhere in this game, I found some kind of Bechdel transformations relating this formulation with this, but it's a fake, slightly fake. I mean, the good thing is you have one physical solution and you get a new, different solution. That's a true Bechdel transformation. I just get different formulations and some semi-Bechdel things, but okay, 1 minute only. Yeah, so everywhere. So for instance, if you ask what's the relation of tau, mu, t, and phi, you find out that tau dot is u prime, and tau prime is R squared mu dot, or something, either 1 over R squared or R squared. And zeta and kappa, so this zeta is equal to kappa prime, and this is kappa dot over R squared. So everywhere where you look at these axisymmetric membranes, you always find pairs, either the pair Z and V, or the pair tau and mu. So here dot and prime is with respect to t and phi. And here zeta and kappa. And so there is some kind of, and it transports. So this kind of Bechdel transformation I found is that despite of this non-linearity, you can go and go and go, but it's not ideal. So, okay, time is up. And the most simple question is, does anyone have an idea what the physical geometric meaning of this E could be? I mean, it's clear if that satisfies this, there has to be such a V. But geometrically, I mean, R then have a clear meaning. This is the radius of the surface, then is the Z component of the surface. And my question is, what is the geometric meaning? Thank you. And I hope, I mean, maybe the most interesting part is the message is in principle, I think I know at least to produce quite a lot of solutions of these equations. And as we agree that these are interesting equations, it may be useful to find expressions. Of course, this I did now only in 3 dimensions, and you need 11 dimensions, and you need supersymmetry and so on, but it's the beginning of finding explicit solutions of that. And thank you for giving me the opportunity.
Thank you very much, Denjo. Thank you to Jens also for inviting me. And Jens is kind of the reason that I'm here to talk to you about this problem about quantum minimal surfaces and how it's connected to discrete Painleve equations. So he's already done quite a good introduction to the topic, but I'll still try and go slowly, fairly slowly. It's the end of the afternoon, so I'll introduce everything quite gently, and also maybe I know there's at least one person that wasn't here for the rest of the talk, so I'll try and introduce the topic more or less from scratch. So this is some work that I've completed quite recently with 2 of my colleagues from Kent in Canterbury, Peter Clarkson and Ben Mitchell, and then also with Anton Jamai, who's recently moved from Colorado to BIMSA in Beijing. So I have a small number of slides, in fact, and then I'll probably also write quite a few things on the board to explain in a bit more detail. This is sort of actually a version of a talk that I originally gave in Tokyo to a mixed audience of graduate students in physics and mathematics and science generally. So it's good. The slides should be quite easy watching. Unfortunately, there's some audio visual problem that hasn't worked out. That I'm not very good with the technology. But originally there was meant to be a little animation of a moving surface. You're wondering what this empty box is here. So this is a minimal surface, and then these are some blow-up diagrams which are related to discrete Painleve equations, which are some divisors in P1 cross P1 in the plane. And this is the geometry of Painleve equations, which I'll come on to in due course. But okay, just because I couldn't get the thing to embed properly, so I've just kind of found this for you. So this is sort of what should have been more or less in there, is a little animation. So this is actually a catenoid deforming continuously into a helicoid surface. So this is like a one-parameter family of minimal surfaces in R3. So you can see a helicoid surface, which is a minimal surface in R3. And then if you look, it goes through, there's a catenoid in the middle. So that's anyway, that's what's meant to be in that box that's missing. Okay, so we can go back to the slides.
Oh, this was very important, indeed.
What's that?
I just realized something, because the quantum helicoid is completely different than the quantum catenoid.
Yes.
And I was just wondering how that fits.
Well, that would be interesting. In fact, I will probably say something when we come to that part about your comment about the catenoid, because it actually fits in what you said, fits in with sort of my understanding. So I'll come to that anyway. So this is, well, as Jens kind of told you, this is something that he's been working on for a while, and then he got in touch with me about 2 years ago, and we started a nice online communication. And I had various hunches about how to explicitly solve this specific quantum minimal surface problem, or this double bracket equation, or King's equation, or however it's called, which I'll explain. Well, not King's equation, but anyway, the double bracket equation. Okay, then the other thing is that when I first gave this talk in Tokyo, and I dedicated to my friend and colleague Masatoshi Nomi, who is an expert in the theory of special functions and representation theory of quantum integral systems, and also Painleve equations. And Nomi Sensei has this very nice book about Painleve equations, which is a very good book for students if you want to learn about Painleve equations. So a lot of this talk is going to be kind of propaganda for Painleve equations, and why they're interesting, why I think they're interesting and useful, and again aimed at somebody that doesn't know anything about Painleve equations. So I'll just say some very simple things about Painleve equations, but this book is a very nice starting point, and also going through the Hamiltonian theory, and also many beautiful results about symmetric functions and determinants, which come into the theory as well. So that's a very nice book to start with. So, oh, I'm sorry, before, I just want to point out that does anybody recognize the woman behind on the wall?
Yes.
Yeah, Kovalevsky. So yeah, Sonia Kovalevsky. So she also is very important in the story of Painleve equations.
The images are slightly clearer on this screen.
Yes, maybe, yeah. Sorry, it's not very clear, I guess, because
It's okay.
but it's all okay. You can look on that side if it's not. But okay, so yes, so these 6 ordinary differential equations called Painleve equations, P1, P2 up to P6, and they're all second order nonlinear ODEs of a specific kind, of a specific structure. So you have the second derivative on the left-hand side, and then you have some function of the first derivative and the dependent variable and the independent variable. and you normally require that it's a rational function of the first derivative and an algebraic function of W and an analytic function of Z. And the problem which Painleve posed was to classify all of such equations which have the property that all solutions have no movable branch points, or maybe to say that all of the movable singularities of the solutions are poles. So if you're not sort of familiar with thinking about ordinary differential equations in the complex plane, or probably you're familiar with linear ordinary differential equations. So the things about with linear ordinary differential equations is that they can have singular points which are fixed by the coefficients of the equation. So when you do Frobenius method and you find local expansions, you find initial equation, and you find indices, and that the places where the equation can have branching are fixed by the coefficients. So that's a standard theory of linear equations. But if you have nonlinear equations, so if we just go to there's a first order, and you think of this very simple first order differential equation, well, the general solution of this equation is just a rational function with a simple pole. But the point is that the position of the pole of this Z0, this is an arbitrary point. So this is called a movable pole. So if you look at a general, say just a first order equation, you could just take a different power, a higher power, then you would find again a movable singularity, but it would have some kind of branching, like algebraic branching. So that would fail this requirement that there are no movable branch points, which is now called the Painleve property. So that's the normal name that's given to it. So this classification was done. And so in the first order case, essentially the only thing that satisfies this criterion is Riccati equations with analytic coefficients. But in the second order, it becomes a lot more interesting. So you have this list of, if you like, 6 equations, or really their equivalence classes of equations up to some simple transformations. And you can see, well, they're not maybe it's clear on that slide, but they're still very small because it's quite hard to write them. But they're some nonlinear equations, and they're non-autonomous because the dependent variable appears explicitly on the right-hand side. And also they generally have some parameters. So P1 has no parameters, but P2 has a parameter called alpha, and then the other parameter equations are put in alpha, beta, gamma, delta in various places. So they depend on parameters. And so Painleve actually found the first 5 equations, and then Richard Fuchs found the 6th one from a different Painleve kind of missed number 6, which is the most complicated one. So just to sort of focus on one of them, the simplest one, and I'm afraid I've changed the independent variable from Z to T, but it's still the same equation. So this is called the first Painleve equation. And Kovalevsky really also developed this kind of analysis of analyzing nonlinear ODEs around singular points, and she used that to actually find a new explicit solution of the problem of a rigid body rotating freely around, rotating around a fixed point under gravity. So she basically assumed that the solution would have Laurent series expansions, and that allowed her to isolate exactly which ratios of moments of inertia would be solvable in meromorphic functions. And so she recovered well-known cases of Euler top and Lagrange top, but she found a new rigid body solution, and she was able to then explicitly integrate it in terms of meromorphic functions, actually genus 2 theta functions. So that was a kind of tour de force of 19th century, late 19th century analysis. But now you can just sort of, there's this rather algorithmic approach, so it's often called Painleve analysis or Kovalevsky Painleve analysis, that you can just look for leading order behavior in the equation. So in this equation, if you want a singularity, then you can see that the leading order has to be a double pole, which is movable. This point P0 is arbitrary, it can be whenever you like. And then you can expand locally into a Laurent series around that point. So that's a bit like Frobenius method. It's just like a nonlinear version of Frobenius method. And then you can find a general kind of two-parameter solution locally given by this Laurent series. So that's a sort of local analysis. That doesn't prove globally that it's meromorphic, but the solutions are meromorphic. That's a harder problem, but at least locally that passes this local test. And you can also think of this, so this is rather like a non-autonomous version of the equation for the Weierstrass elliptic function. If you know Weierstrass functions, if you replace the t by just a constant, then the Weierstrass p function satisfies the same equation, but this t would be constant minus half g2, one of the invariants of the Weierstrass function. So this is kind of like a non-autonomous deformation of an elliptic function, and it's known that all of the solutions are meromorphic transcendental functions of t, and they can't be written in terms of any simpler analytic functions like solutions of linear differential equations or elliptic functions and so forth. So that's just a sort of brief introduction to a Painleve equation. And then, well, I like this. There's a phrase that my colleague Peter Clarkson has used as all part of propaganda for Painleve equations, because he, in the NIST digital library of mathematical functions, he wrote the chapter on Painleve equations, which is kind of like a handbook. It's like the online version of Abramovitz and Stegman. Unfortunately, with the new US administration, at some point, the digital library went down. And I think it got restored in a couple of days. But when I was actually trying to look up something about Bessel functions, it actually had gone down, you know, just when they were cancelling grants and all these things were happening. But anyway, that's a good place to look for more information about Painleve equations. But the phrase that he likes to say is that they're nonlinear special functions. So you're familiar with, you know, Bessel functions and hypergeometric functions and things that when you solve linear PDEs by separation of variables, you find all these classical special functions. And the point is that there are lots of nonlinear problems to do with things like wave breaking and dispersive shocks and all kinds of problems, and also scaling in random matrices and statistical mechanics, orthogonal polynomials, and quantum gravity, which is very well known to this audience with matrix models. Where actually the scaling behavior is described by Painleve equations. So a sort of example from the end of the 80s is the correlation function of the Bose gas. So you take if you take particles, you know, interacting with delta function, nearest neighbor delta function potential on the line, and then you take a thermodynamic limit, that's called the Bose gas. And the correlation functions of that were described in terms of some special solutions of the Painleve 5 equation by Jimbo, Miwa, Morisata. I think that's about 86. So that's one of the examples of applications of Painleve equations in these kind of problems. And then another sort of more recent thing which has become rather widespread is actually in sort of combinatorial and probabilistic problems. And there's a particular set of probability distributions which are known as Tracy-Willem distributions, which come from solutions of Painleve 2, and they're actually related to the airy kernel, which was sort of mentioned a bit in one of the talks that I watched online on the first day. But anyway, the Tracy-Willem solution of Painleve 2, so there's some special classes, and they appear in from scaling limit of two classical random matrix called the Gaussian unity ensemble and the Gaussian orthogonal ensemble. And they also really can be experimentally detected when you look at liquid crystals. So these two pictures, well, these two represent fluctuating surface of a liquid crystal. The height function, which determines the distance, there's all these kind of oscillations or sort of variation around the edge. So this is like a droplet of liquid crystal, flat droplet, and then this is like a flat plate with a liquid crystal spread out horizontally, and then so this is sort of like on a circle, coordinate on a circle, and this is sort of on the real line. And these are actually, again, I think maybe it's easier to see on that screen. This is the droplet, and this is the flat plate. And the first one, the droplet, is described by the Gaussian unitary ensemble statistics, and the other one is described by the Gaussian ensemble statistics. And these have been compared exactly with the Tracy-Willem distribution corresponding to each of those ensembles, and it matches extremely well. And so there's a group which is sort of German-Japanese collaboration, Spohn and then Takeuchi and people in Tokyo that did these experiments, and they really match that. And it also is related to a solution of this interface growth problem. It's described by the Kada-Parisi-Zhang equation, this stochastic Burger's equation. And the solution, so it's a stochastic equation, the solutions are given by probability distributions, and these Tracy-Willem distributions exactly give you exact solutions of the case equation. So
it's the edge of the distribution.
It's the edge of the distribution, it's the edge statistics, that's right. Yeah.
And another case where I got stuck with it was that there's a Hagedorn transition.
Oh, okay.
In models where the Painleve crops up, which is.
Oh, okay. I'm not so familiar with that one. So yeah,
I'd like to talk to you.
Yeah, let's talk about it later. Okay. So anyway, that's all propaganda for Painleve equations to show you why they're interesting and useful things. But this is where they came up in this problem that Jens showed me. So I think everybody, I don't want to teach my grandmother to suck eggs, is the phrase that you say in English, because everybody in this audience is an expert in the Schill's function of them. Actually, when I was talking to some mathematicians recently that giving this talk, they know differential geometry, but they weren't really familiar with this way of formulating normal surfaces with this action. So the action, I mean, just to write it down. So you have your surface sigma, and then you have this cosine bracket. So you can think of your surface. So we have a map into D-dimensional Euclidean space. Everything's Euclidean here. And the pictures that I was showing you in the little animation, that was all the case D equals 3, which is the classical case. And so you can think of locally, you can have some coordinates QP on the surface, and then that gives you this map to the functions x1 up to xd. So the coordinates of this vector in Rd, which will be functions of q and p. And so if you write down this, and then this is the symplectic form, the area form on the surface, and this is a completely invariant formulation of the problem. So if you have a symplectic form, non-degenerate 2 form, then you also immediately have the Poisson bracket on the surface. And so the equations of motion, you do the variational problem, and the Euler-Lagrange equations are exactly these double-commutator equations. So let's look at it like this. If I didn't, yeah. Okay, so the classical case that's well known and was sort of completely solved by Weierstrass is the case D equals 3, and even Lagrange wrote down this equation. So if you think of the surface as just a graph of a function like this, then Lagrange wrote down this form of the equation. So you can plug that into the action, and it has a very nice kind of symmetrical form. So that's the Lagrange form of the minimal surface equation in 3D. However, that's not going to be the case that I'm going to be interested in. If you were listening, really paying attention to Jens, I'm really interested in the case D equals 4. So that was the case But then not only that, but to also quantize it. So again, not maybe the grandmothers and sucking eggs. But of course, you all know what quantizing is. But for mathematicians, I sort of say what it's going to be. So if we just had our conjugate Q and P, the canonical conjugate Q and P, then there's the Heisenberg commutation relation. And now, so if we think of these xj's, these are real functions, and then we want to replace them by permission operators acting on some Hilbert space, and then we have this double commutator equation for the operators x1 up to xt. So that's exactly the quantum equations which we've seen many times. And yeah, so if you like, I first learned it from this paper of Arnold Hoppe and Kawai, which actually preprints, not published, which is a shame. It should be published, but anyway, it's a great preprint. And then also there's as Jens did a great bibliographical job. So there's Conalber and Taylor, and then IIKT, who's read many times in the case of Minkowski. But okay, so I won't go into the bibliographical details any further because we've seen it a few times. So okay, so that's the problem. And then now, as I said, I'm really interested in the case d = 4. So and this is exactly as Jens was saying, it's Eisenhardt around 1905, I think, is the paper, which is that a particular solution of the minimal surface equations in 4 dimensions is obtained by taking a Riemann surface in C2. So you identify C2 with R4, and then you can take the complex coordinates Z1 and Z2 with real and imaginary parts x from x2, x3, x4. And so then you can just think of the Riemann surface, that's 2 real equations, and that's in R4, so that's a surface in R4. And the point is that automatically gives you a solution of those double plus and bracket equations. And the way that I think of this is, first of all, because Z1 and Z2 are functionally related, their plus and bracket is trivially 0. And then, okay, there's a sort of, this is the King equation. I think this is related to your point about fixing G to be a constant, is that if you have a Riemann surface, you kind of have a conformal class of metrics, but you can fix a metric with a constant Gaussian curvature, and then you find that Z1 and Z2 are their complex conjugates satisfy this bottom bracket equation, where kappa is basically the curvature. So that's just a sort of calculation. And that's exactly the sort of classical analog of the equations that Jens was writing down. So the point is that you automatically, then you quantize it. So you automatically have, that these 2 operators commute, and then the quantum version, which, yeah, we got again mentioned Kontsevich and his student, well, this non-commutative King's equation, but so you have this equation, which is for the operators and their emission conjugates. So if you have a relation between Z1 and Z2, then this one is satisfied automatically. So again, we can think of 2 operators that are algebraically related. And so then the non-trivial equation is this one that we need to satisfy. And so then the so then well, let's speak. So the main example, I like to say, is the quantum parabola. So again, Jens already did a very good job of introducing this problem. So if we just call Z1 W and Z2 is W squared, so we sort of have one operator parameterizing. It's a rational curve, so we can parameterize it rationally. So this gives you the relation, the parabola equation. And then now we have to, and we need to satisfy this this equation. And okay, and when you look at the semi-classical limit, which Jens mentioned a little bit, then you also find that this parameter epsilon is sort of proportional to the Planck's constant as well. That's sort of useful for fixing things semi-classically, what the solution is going to look like. Okay, so then the problem is we need to find a Hilbert space where this operator W can act and satisfying this commutator equation. So so we just take just a thing like an oscillator, a single boson with a ground state, and then W acts like a raising operator, and then W dagger acts like a lowering operator, and we have this multiplier Wn. So that's where this is where the discrete Painleve equation is going to come in. So you have W acting on the ket, N is Wn times n plus 1, so that's the raising operator, and then W dagger acting on N is going to be W n minus 1, n minus 1. And then we need to have a ground state, so W minus 1 is going to be 0. And then if you sandwich that between, so if you sandwich this equation between a bra and a ket, then you get. Can everybody see actually where I'm writing here? Is that okay? You can. I don't know if you can. It's all right. So if you sandwich this commutator equation between the bra and the ket, then you get a third order difference equation for the modulus squared of Wn. So Vn. So this is again, Jens kind of wrote down something but didn't explain all the details. It wasn't his main point of interest in that talk. So Vn is the modulus squared. And then if you just do a short calculation, you'll find that this commutator equation gives you this equation for Vn, which is a third order difference equation. And then if you look at that closely, you'll notice that the left-hand side is a total difference, right? So you've got the difference of Vn and Vn minus 1. And then you've got, if you insert kind of Vn minus 1 minus Vn minus 1 in the middle, and this thing is also a total difference. So you can integrate it, or sum it, if you like. So the opposite of differencing is summing, or discrete integration. And then you'll find this second order difference equation. Sorry. So this is what's called the discrete Painleve 1 equation, but it's actually a terrible name, and I'll explain why it's a terrible name in a minute. So this is the main problem then, is if we have this operator equation and we want to find a solution, then we need to find a solution of this second order difference equation. And there's also, we integrate it, so there was an integration constant. The integration constant is fixed when n equals minus 1, because we have to have v minus 1 is 0. So v minus 1 is modulus squared of w minus 1. So that's fixed to be 0. And then the whole problem is determined now. It's a second order difference equation. We've already fixed one of the initial conditions has to be 0. And then v naught is some value, but also it better be positive because it's the modulus squared of w0. So the initial value problem we have to understand is solving this second order difference equation with 0 initial, but 1 0 initial value and another positive initial value. But then we require that all of the subsequent iterates also have to be positive. So this is the problem that we want to solve. And Jens mentioned a little bit also that there's a nice kind of semi-classical limit. So you can think about actually sort of large n, not just h bar going to 0, but also n going to infinity. And if you sort of say that Vn and Vn plus 1 are approximately the same order of magnitude, then you just get a quadratic equation for Vn, just an algebraic equation. And then the solution, the sort of approximate solution of that quadratic equation is this, which also satisfies the initial condition that v minus 1 is 0. So that's quite that's a sort of useful approximation, and also to first order and second order and epsilon, it actually agrees with what you want from semi-classical limit, but then it doesn't work. It's not the solution. It's just a sort of asymptotic solution, roughly. So, okay. And then just to make a comment about Painleve and discrete Painleve, what does discrete Painleve mean? So I told you, I gave you a sort of definition of what Painleve equations are, but I didn't say what discrete Painleve equations are. And actually, that's a sort of really a question that's only been defined properly, you know, more recently than a lot more recently than Painleve. But the point is that in all of these applications, like orthogonal polynomials and random matrices, people found different analogs of the continuous Painleve equations, and they introduced a nomenclature for them, which was actually very bad, because all of those equations that have been found, they have some continuum limit, if you think of doing finite differences. And so it's a little bit messy, but for this equation, you can do a finite difference limit. So you sort of treat t as n times a small displacement, and then take the limit when n goes to infinity and the displacement goes to 0, so it's only finite difference. And you can find a continuum limit, which gives you that continuous Painleve 1 equation. However, the problem is that there are many difference equations that have a nice structure, an integrable structure, which are also have continuum limits to Painleve 1. So this is a discrete Painleve 1 equation, but one of many that are known. So the problem is, which one is it, and how do you understand that? So the answer really comes from geometry, but let me tell you a bit more about this this unique positive solution. So Jens actually in the paper with Arnold and Hoppe, they actually showed that a positive solution with this initial value problem does exist. So for all epsilon greater than 0, there is a positive solution of this problem for all n. There is a for all n greater than 0. There is a solution, but they couldn't show that it was unique. So this is the part that I actually sweated on the most, but my colleague Peter Clarkson and another colleague Anna Loureiro and Walter Van Ascher, they had studied some other discrete Painleve equation with a positive solution, and they'd also proved existence and uniqueness. So I tried to mimic their argument, which was by a kind of contraction mapping argument. So the idea is that you introduce a fixed point problem related to the discrete Painleve equation. So let me scrub out a little bit. So if you rearrange the Painleve equation in the following way, this is sort of a strange way to write it, because if you were thinking about solving this equation, you want to be given the previous two iterates and then find Vn plus 1. So this is, to a normal Painleve person, this is a rather strange thing to do. However, the point is that this naturally allows you to set up a fixed point iteration on sequences. So you think about a sequence, an infinite sequence, semi-infinite sequence of sort of u0, 1, 2, and so on. And then you also try, well, at least this is the first guess of putting a norm. So a kind of L infinity norm. Well, everything's positive, but you can think about any sequences. And then you try to set up a fixed point iteration, which will converge, which will be a contraction mapping with respect to this norm. And then the Banach fixed point theorem would tell you that it's a unique fixed point. So that's sort of the idea. So the what you define is that the new sequence TUN, the nth term of the new sequence, is given by just this, just putting, you know, whatever your sequence is into this machine and getting the answer. And this is a nice sort of mapping to do, because it sends non-negative sequences to actually to positive sequences. So it's a nice iteration. And Konalver and Taylor also sort of thought about something like this, although they didn't really describe it explicitly. And numerically, it works very well. So this is a good way to find the positive solution. For each epsilon, you can iterate this, and it converges very fast. And also, why is it good? Well, so we know that there is an exact, in fact, that now that there is a unique positive solution of this problem, and we can even write it explicitly in terms of Bessel functions, which is just sort of in Jens's talk, and I'll show you on maybe the next slide. But the problem is that if you put that into 10 decimal places accuracy, and you iterate the Painleve equation with starting with 0 and then your V0 given to 10 decimal places, you don't find this solution, you know, after about 3 iterates, it just goes negative and starts oscillating wildly. So it's a very, very sensitive initial value problem, this to find it. So, you know, a normal sort of shooting method doesn't work well if you try to do it with just shooting, you know, up and down in U0. This is really the good way to do it. But unfortunately, the Lipschitz constant for this is bigger than 1. It doesn't quite work. So you have to sort of really mess around, and I'll try and just quickly show you what happens. So this is V0 against epsilon. This is the numerically computed solution for V0 for epsilon going from 0 to 5. This is that sort of square root approximation on the lower curve, and this is just the straight line epsilon, and that's just an upper bound. And then what's interesting is that if you do this this iteration, it actually gives you an infinite sequence of rational approximations to Vn. So what it gives you is like the first approximation is that Vn is approximately, or I suppose I can write it up here. Vn is approximately epsilon over n plus 1, but then you can plug in that approximation back into the denominator. So the next approximation will be epsilon n plus 1 over 1 plus 2 epsilon n plus 1. And then, anyway, you get an infinite sequence of upper and lower bounds, so rational upper and lower bounds in epsilon. So this shows, this is that same graph epsilon, and this is the next upper bound, but it goes alternately upper and lower bounds. And it's easy to prove that the upper bounds are decreasing and bounded below, and the lower bounds are increasing and bounded above. Unfortunately, it's not easy to show that they squeeze in the middle. That's really the hardest part. And I'll try and, right at the end, I'll try and explain how you show that. But you can also calculate an asymptotic series for V0 of epsilon, so and for all of the Vn's. And there's like a complete expansion. And but anyway, the problem is, how do we actually characterize this solution? So this is where my friend Antoine comes in with geometry, and this is the Sakai scheme for classifying both continuous and discrete Painleve equations. So the idea is that Painleve equations have singularities. We've already seen poles in Painleve 1, and also these difference equations have singularities. So for example, if you rewrite this for Vn plus 1, and then you have to divide by Vn, then you'll see that if Vn is 0, like this initial condition, then you have like a pole in your initial data. So there is a question about how do you kind of analytically continue, and the way that you do that is you think of it as the difference equation. Each iteration is a map on P1 plus P1, and then you have to do a blowing up procedure, adding some copies of P1 at singularities, and you can do what Sakai showed is you can classify all of the equations that you get from doing 8-point blowups of P1 plus P1, and they have a very beautiful structure in terms of Dinkin diagrams, so actually affine root systems, and this is characterized as the surface type. And the one that we're interested in is D51. So this is what Anton found from the calculation. So D51 is actually the surface type of Painleve 5, the differential equation, but that's also the surface type of this discrete equation. So that was this kind of hint, the strong hint that actually they live on the same space of initial conditions, and that therefore this difference equation should correspond to a Backlund transformation of Painleve 5. And then, okay, there's a whole geometry here that you have a smooth rational surface, which is obtained from this blowing up procedure. It's a generalized Halfman surface, and then you have an effective divisor. So that's like just if you like, a sum of a positive sum of linear combination of curves, and that's what gives you this a configuration of curves with intersections, and the intersectional indices determine the Dinkin diagram, saying like intersect, inner products and roots. So one of them, one root system you get is the surface type, which is this picture, and then there's a dual picture, which is an orthogonal root system, all living inside the E81 root lattice, which determines the symmetry type. And for Painleve 5, that's A31. That's the symmetry type of Painleve 5.
What is the genus of the divisor?
The genus of the divisor, wait a second. I think it's 1. I'm trying to remember. I think it can only be 0 or 1, and one case corresponds to elliptic surfaces, and the other one corresponds to these generalized Halfen surfaces. So, but I've forgotten which one it is. I have to check. Okay. Yeah. But thank you. Yeah, that's a good question. So these are the two sort of complementary Dinkin diagrams, D51 and A31. And then this, just to remind you, this is the Painleve 1 differential equation. And then basically doing this procedure, you can kind of get a canonical representation of the surface and nice coordinates. And so you can actually show that the solutions of this difference equation correspond to a sequence of solutions of this Painleve 5 differential equation with these parameters alpha, beta, gamma, or alpha, tilde, beta, tilde, and so on, given in terms of n. And then also the solution W, this Painleve equation, is related to Vn by Mobius transformation. And then the independent variable t is just related to epsilon, that parameter, by 1/3t. So that's what kind of the geometrical calculation does, or that's how Anton did it. And then also my other collaborators were very good at kind of working directly with background transformations, and they confirmed exactly the same results from things that you can look up in the digital library if you look up the special solutions of Painleve 5. So then the point is that although general solutions of Painleve equations are transcendental, on some hyperplanes in the ground space you get classical solutions. And in P5 these were known to be given in terms of Whittaker functions or equivalently Kummer functions, and they were sort of studied by Masuda, and they're a determinant, kind of Wronskian determinant formulae. But actually what my junior colleague Ben Mitchell in his PhD has been doing is he's been able to write some of these Whittaker or Kummer functions in a simpler way in terms of Bessel. So the point is that you find that in these special ground spaces, you get a Riccati equation. So actually V0 satisfies a nice Riccati equation given here. And that gives you a one parameter family of classical solutions. And then if you linearize the Riccati equation, you get two independent solutions of Bessel, modified Bessel equation. But it's only the Bessel K which satisfies the positivity condition. So within this one parameter family, there's exactly one solution which has the correct asymptotic expansion in epsilon that gives you the, first of all, gives you V0. And then if you prove the uniqueness and positivity, you prove that it gives you the unique positive solution. So this is also the unique positive solution of the Riccati equation, which is positive for all positive values of epsilon. So the theorem then is that those initial conditions in terms of ratios of modified Bessel functions give you the unique positive solution of this quantum parabola equation. So that's the kind of main result. And I'm just seeing if I'm doing time, because I think I started a little bit late. So I've got a little bit of, I've got 10 minutes definitely. So even 15. Okay, I mean, that's good. I'm comfortable. Okay.
I must interject and say, Whittaker, I presume this is the Whittaker and Watson.
It is indeed, yeah.
He spent many years as chair of the board of the School of Theoretical, or involved in this board of the School of Theoretical Physics. He wasn't actually chair.
Okay. Thank you.
Yeah, and he was very influential in founding the institute.
Okay, thank you. I didn't know that. Oh, great. Yeah, indeed, it's the same Whittaker. Okay, I think this may be my last slide. So that's good. So that means I can indulge myself a little bit. So I can tell you a little bit more about this unique positive solution, because the key, from my point of view, the key was actually that I've been thinking a lot and working a lot on problems related to continued fractions recently. And the point is that, well, this, as I said, this iteration gives you a sort of gives you an infinite sequence of rational approximations. So the next one will be so you can kind of see you're substituting in the previous rational approximation at one level into the next one, and you alternately get upper and lower bounds. But this is a rather strange thing. This is kind of like becomes a branched continued fraction. So it keeps branching and branching and branching, which is rather complicated. But the point is that if you just start with V0, which has this asymptotic series. Anyway, one go on, but anyway, so you can just calculate this asymptotic expansion, which also Jens was working a lot with this. The point is that there's a natural way to approximate an asymptotic series in kind of Padet approximation, which goes back to Stiltz's, which is that you can, if you have such an asymptotic series, you can approximate it by a continued fraction. So the continued fraction in this case is very beautiful. And I think Jens is going to sleep, but anyway, you can guess what's the next. So it's going to be 1 plus a multiple of epsilon. So can anybody guess what will the next? So it's 1, 2, 4, 5. So what's the next number in the sequence? Anybody guess? Okay, well, I'll help you then. The next one is 7. So what's the next one?
We usually go to the encyclopedia, the online.
Yeah, well, no, this is a very simple. No, this is a very simple sequence. So okay, 1, 2, 4, 5, 7, 8. So it's basically everything except the multiples of 3. So you just count, but leave out the multiples of 3. So the point is that this continued fraction is exactly the exact representation of this ratio of Bessel functions, and this positive solution of this Riccati equation. And so, I mean, this is Stiltz's method for calculating continued fractions, but actually, this type of fraction is very special. It actually goes back to Euler. So I didn't realize, but Euler created continued fractions in order to solve Riccati equations. I always think of, I mean, I only learned continued fractions relatively recently, but you know, in number theory, you think about rational approximation of real numbers, but actually Euler created the theory to solve Riccati equations. And this Riccati equation is a type of Riccati equation of the kind that Euler was studying, and Lagrange and Bergfinnur. So it actually has a very beautiful structure that you see. What you do is epsilon. You have epsilon, and then 1 plus v1. So that actually comes from iterating this when with v minus 1 is 0. And then v1 is given by this continued fraction, and that also satisfies a simple Riccati equation of this type. Now, it doesn't keep on being quite as simple as that, because then you have this sort of branching behavior. But the next one is 2 epsilon, and then v0 plus v2, but v0 plus v2 also satisfies a very nice Riccati equation. And then it kind of goes on. There's more terms, but each of the 1 plus something and the something satisfies, you know, a very simple pattern of Riccati equations. So there's an infinite sequence of Riccati equations that describes this continued fraction, and that's what Euler, one of the type of fractions that Euler discovered. So now the point is that if you know about Padet approximation, then Padet approximation also gives you, or continued fractions give you a sequence of upper and lower bounds, and then you know that those things. I mean, it's easy to prove that they converge to something positive in this case. And then what you have to do in the end is you compare these rational approximations with the ones that come from the classical continued fraction, and actually they interlace each other. So because you know that the classical continued fraction squeezes in the middle, then you know that this iteration squeezes and gives you a unique, first of all, V0, and then the uniqueness of V0 then tells you the uniqueness of V1, V2, and so on. So that's kind of the argument for uniqueness.
And how do the Paddy approximations fit into this argument?
Well, these are the Paddy approximations are the truncations of this, and so the first two approximants agree with what you get from this fixed point method, but then after that they sort of interlace rather with the other rational approximations. So in Paddy approximation, you're only approximating up to a certain order in epsilon. You're only up to and so the point is that each of these things is giving you two approximants to the same order in epsilon, but one of them is slightly better or slightly worse. So that's how
it's for the error analysis.
So it's the error analysis in the end that does it. So some inequalities with the errors. So that's what gives the uniqueness. Now, yeah, I have a colleague who's really an expert in functional analysis, and he said, well, maybe the problem is that the norm that you're using is not the right norm, and there's probably a better norm, and maybe there's a nice way to make this argument simpler without having to do such delicate sort of Paddy type analysis. But okay, so just to sort of come to the conclusions, and some of this is already answered actually in Jens's recent paper with Giovanni Felder, but well, actually the first thing, yeah, so the point is that we know other examples like this which are related to orthogonal polynomials. So this talk was from February, as I said, and since then, lo and behold, Hoppe and Felder have exactly connected this solution to some orthogonal polynomials which are related to normal random matrix models. So that kind of answers this part, that indeed there is a sequence of orthogonal polynomials that reproduces this that gives you the solution. Then the other thing is to look at other, just let's say, rational curves. So if you have these operator equations, you can write down an algebraic relation between the operators. And then, for example, if you take, we looked at the parabola, so 1, 2, but then if you look at 1, 3 or 2, 3, then you get a different rational curve and a different minimal surface classically. And actually you get an analog of this equation, but in both of those cases it's fourth order. So that's like a fourth order analog of the discrete Painleve equation, but unfortunately there's no analog of Sakai's scheme for higher order Painleve equations. So in fact, now I would kind of turn this on its head, that now we have some higher order Painleve equations, and then now we also can construct some explicit solutions of them and relate them to, say, polynomials and matrix models. But also maybe we can understand something about the geometry of higher order Painleve equations as well. So that's sort of the long-term goal, and that's where Nomi comes in, because Nomi and Yamada wrote down some very nice differential Painleve systems of higher order that are related to initially affine type A symmetry. So A2-1 is Painleve 4, A3-1 is Painleve 5, which is the one we saw, and then but they have like what's called symmetric Painleve systems, which are related to the symmetry type is AN1 type. So really the question is, can we understand the geometry of high order Painleve equations in discrete Painleve equations? So that's sort of like a long-term program that we would like to work on. So that's kind of a good place to stop. But thank you for listening.